the hell? How are we looking? Is it looking good? Let's see. Okay, so let's get going. Unless everybody wants to sneak up and get another chocolate bar. You have like 10 seconds. You can go. You can make it. Okay. Okay, so thanks for coming in on our reading week. And for those watching this in the recording, it's all good. So we're going to talk today about logic block architecture. Before that, your current background reading is, so it was assigned last week. You still got another week for it. So just a reminder, we've got these two papers, second half of the survey paper, and the paper that introduced fracturable LUTs, which we'll talk about today. So they're both due on a week from today, and assignment 2 is also due a week from today. So hopefully it's all going well and it's not too stressful. Okay, so what are we talking about today? So we started talking about FPGA architecture styles, then the low-level circuitry, and now we're going into the details of what's inside an FPGA, like going further still. So we're looking at inside the logic blocks. Okay, so the dominant logic block is what I call a logic cluster. Okay, so what's a logic cluster? Well, you have a bunch of logic elements, and in academia we usually call them basic logic elements. And the most common logic element is a k-input lookup table. Okay, so here I'm showing a 4-input lookup table, and it feeds a D flip-flop. And there are a couple different ways you can build this. Here I'm showing you could select either the registered or combinational output. Most architectures now, you actually have enough outputs coming out of the logic block that you can basically take both of them. Okay, so it's not necessarily this kind of zero-sum game of get one or the other. Okay, so early island-style FPGAs just took a LUT and a flip-flop like that, and they basically surrounded it with island-style routing. But nowadays, it's much more common to do the kind of hybrid architecture where we have a little bit of hierarchy to make a more complicated logic block, and then we take those logic blocks and we surround them with island-style routing. Okay, so we take this small basic logic element and we put n of them together with some local routing. Okay, so local routing could be a full crossbar that takes the outputs of all of these little logic elements and allows you to feed them back to any inputs you want, and also takes some number of inputs, I, that come in from the main routing, right? Like the island-style segmented routing between logic clusters, and allows those I inputs to be flexibly connected into whatever you need on the BLEs. Okay, so originally, well, there are a lot of variations on this. So you could do this as a full crossbar, which takes quite a bit of area, or you can do something, a more complicated switch network that doesn't guarantee you can connect all of these I inputs and N outputs back to these BLE inputs, but has lower area. Most architectures now use essentially some form of partial crossbar. Okay, so a partial crossbar means it acts like a crossbar, but you remove some of the switches. So Intel and Altera, well, Intel/Altera FPGAs, if you go back far enough, they did use full crossbars. Now they usually use essentially a half-populated crossbar. So what that means is you take half the switches out. Okay, and we'll talk a bit more about that later. It means there is now the possibility of this getting blocked, but as long as you don't try to put too many signals through it, it's usually okay. Xilinx builds an even more complicated local routing, just kind of like a multi-stage switching network. They've never disclosed all the details of it. So it's, again, behaves like a crossbar, but it has fewer switches, has some chance of being blocked. But as long as you basically don't try to get too many inputs through it, it usually doesn't block. That's why they're useful. Okay, in the academic works we're going to talk about today, though, they assume a full crossbar, which is reasonable as long as your cluster is not too big. But the latest commercial architectures usually take some of those switches out to get better area efficiency. Yeah, Alex.
You mentioned this was a hybrid approach between island style and the hierarchical style.
Yeah.
I'm actually struggling to see the hierarchy here. Why aren't we seeing...
Well, the hierarchy is really flat. So I guess the idea is like this would be level 0. Okay, and this would be level 1. And that's it. Okay, so this is not a giant company. This is a company where there are employees and there is a manager. That's the end of the hierarchy. Okay, So you have a little bit of hierarchy, and then the rest of it is constructed by replicating these logic clusters in a 2D grid and hooking them up with island style routing.
And too much hierarchy would just cost too much. Is that kind of the idea?
It's basically the things that we talked about before, that the long wires start becoming inefficient. So the only FPGAs I know that go hierarchical all the way nowadays, that go hierarchical through the whole array, are basically embedded FPGAs. There are a couple of companies that make embedded FPGAs where they're not intended to be too big. They're like a few thousand lookup tables, and they can actually make that completely hierarchical. So basically like what we showed on the whiteboard. If you go much bigger than that, all the problems that we talked about of some really long wires and stuff come to play. So you'll see that, like, if I get to, well, I should get to the end of this lecture. You'll see in the latest architectures from Altera and Xilinx, they're diverging a little bit. So you could argue that they're starting to move towards like 2 levels of hierarchy instead of 1, or maybe 1.5 levels of hierarchy instead of 1. But yeah, for big FPGAs, nobody does like a lot of levels of hierarchy. Okay, so this is just kind of terminology. So we're going to be looking at, there are some other logic elements people look at, but k-LUTs are dominant, so we'll look at those today. We have these key variables for a logic cluster. How many of these LUTs plus flip-flops do we put in it? Like how many of these basic logic elements? How many inputs do we bring in? This will always be less than the number of, well, with the structure I showed you, where the LUT feeds the flip-flop, there's no reason to ever bring in more than k inputs per LUT, per basic logic element, because that's the most I'd ever need. If I have n of them, I'm for sure never going to need more than kn inputs for this whole cluster. But to make this local interconnect smaller and to make the interface to the general routing smaller, most chips basically choose to bring a smaller number of inputs in. So you'd never bring more than kn inputs in, but you usually design the architecture to bring in some number I that's actually less than that. And the reason is to save area in this local routing and to save area with the muxes that would connect you into the general routing. Because all these signals here, you know, they really have to go through those routing muxes that we showed how to build last week. Okay, so the local routing does 2 things. It connects our outputs, the BLE outputs back to BLE inputs. Okay, so you don't have to leave the logic cluster if you need to be just reused within it. Those connections are made with basically muxes in the crossbars, so they're actually very fast. And we also can connect these I cluster inputs very flexibly to, you know, these BLE inputs, and there are k times n of those. Okay, so hopefully that was clear. Stop me if there's any questions. Yeah.
We didn't really talk about the number of outputs outside of the...
Yeah, so that's a good question, actually. So I guess in the one I've shown you here, there's only 1 output per BLE, so it's n. So the number of outputs is the same as the number of BLEs. You could, so a reasonably common thing nowadays is that instead of having this mux, you just get rid of it, and you basically bring out outcom and outreg, and now you would have 2 times n outputs. Okay, so that's another way you could do this, and that will make this interface to the general routing a bit more expensive because you've got more things to hook into the routing. But you're also now able to use the register and the LUT more flexibly. You know, you have some ability to do independent use of them. So for the, I guess the main architecture studies that I'm going to show you, the academic ones, there's just 1 output per BLE, so the number of outputs leaving the cluster is n. But you can increase that if you wanted. You could also decrease it, forcing some things to be used inside the logic cluster, and that's been done in some chips. That is generally a pretty bad idea. Altera did that in one of the chips that we had to write CAD tools for when we were Right Track CAD, so we didn't architect it. If you use both the LUT and the register, you could only get one of the 2. Like basically you had 8 LUTs and 8 registers. You could use both, but you could only get 8 signals out. And that was a real pain, right? So, because now you had lots of illegal configurations. So while you can do that, I'd say that's not a great idea if that limit is too tight. Okay, so architecture questions. So what's the best basic logic element? So there are other ones. We're basically going to talk about the LUT ones. And the reason that people mostly use LUTs is, we talked about it already, right? So maybe this is a comprehension question. So why are LUT-based logic elements good? Yeah.
This could represent an muxes table, which would represent the logic function that way, so probably one to capture the functions but since use was as long as that has cadence, logic function has cadence.
Yep. Yeah, so it's a good answer. So it's a very efficient synthesis target, right? If you have k or fewer inputs, the logic function goes in, gives you a lot of functionality for the number of routing ports you have, like the most functionality you could have, basically, like any function with that many signals you can implement. So that makes it pretty good, right? So it's an efficient synthesis target and lots of routing functionality for a few routing ports. Because these routing ports that connect you into the general FPGA routing, they're expensive. You get to choose how expensive, like how big do I make those muxes, but usually to make things route pretty well, the amount of muxing is reasonably large, right? So like a 20-to-1 mux or more would be typical to connect these LUT, like a LUT input into the local routing or into the general outside the cluster routing. So that's pretty expensive. Okay, so then we have the decision of what's the best LUT size. Okay, and we talked about some trade-offs for that too. So what happens as the LUT size gets bigger? So yeah, what are the trade-offs there?
I guess if the lot size gets bigger, you have more routing, so it's easier.
Yeah, so it captures more logic, so you get sort of fewer hops. You have a certain amount of logic to do on your critical path, you'll have fewer LUTs in series. So that's good.
Because routing increases your logic there's more for each one. I guess there's more area around. Also, I guess by extension reduces the pressure on the cluster routing, but then
Yeah, so I'm going to summarize that. So you got, okay, so we get more stuff per LUT, which is good. We get fewer of them in series on the critical path. However, and that we also, because we need fewer LUTs, we wind up with fewer things to hook up to the routing. That actually saves us routing area because we can just implement the whole circuit with a smaller number of blocks. Each block is more complicated, but we need fewer of them. That's all good for area. Sounds great. I mean, so I'm going to make a 1,000,000 input LUT, right? Because you just keep, like anytime there's like just it just keeps getting better, then I'm just going to the max, right? But I don't think you wanted me to make a 1,000,000 input LUT. So what stops me from just going crazy and saying, well, let's just make k approaches infinity?
It'll be slower. Like the individual LUT will be slower. Like
It's true. The LUT itself gets slower.
8 LUT versus like
So at some point where it's captured everything between two registers, then making it bigger just starts making stuff slower and slower. So yeah, that's bad. And it's bigger. And how much bigger? So if I go from like,
you said it's 2 to the k.
yeah, so it's exponential. So there's a pretty hard limit of like it starts getting really expensive, right? To make the LUTs really big.
only a big fraction of the size or something.
Yeah, so that's our trade-off, and it's not clear what the best answer is, right? So anytime you have like, well, I have these two competing forces, so I use fewer LUTs, that's really good. Fewer things on the critical path, that's good. But each thing is getting slower and bigger. Okay, so what's the best choice? It's not obvious, right? We've got some complicated intersection of equations, and it's not obvious what the best value is.
Like, if you're, I guess, improving every process technology, like you're getting faster. This, sort of assuming that you can stay within a certain power budget, Fmax is getting better each time. What stops like companies from design space exploration each time migrating to process technology?
Yeah. So they do some design exploration every time they change process technology, and it depends on the company and how big their R&D budget is, how thorough that is. I'd say for Altera and Xilinx, it's pretty thorough, especially if they won't do as much on every single process node if they're going to do, for example, a 14 nanometer and then shrink to 10. They may just not be able to keep up, right? Like because it sounds, oh, do a design and space exploration, how long will that take? Well, if you need layout models and there's a lot of getting the process data in, it can take a while. And you need some new architecture ideas. So they will do some design space exploration every process node. They may do a lot. And if they don't have time before the next process node comes up, they'll cut it short. And the reason is because, yeah, the technology trends change. The amount of wire delay versus logic delay is changing. The area, SRAM area is not scaling all that well. So that's something that's now starting to happen. And maybe the biggest LUTs are a bit more expensive than they used to be because they have so much SRAM in them. So yeah, your delay and area characteristics aren't constant. And that leads people to retune things. One of the things that fights against that is changing certain parts of the architecture can be very expensive. Okay, so Xilinx says that they spent $1 billion developing the Versal architecture. So they can afford to spend $1 billion. They probably don't want to spend it, they don't want to spend it foolishly. So they can only spend $1 billion, maybe amortized over a couple of years anyway. And the reason it costs $1 billion is you change your hardware design and you explore the space, that's expensive, but then things that fundamentally break the software are very expensive. So you get some things that aren't too bad if the software is parameterized that way. So changing the LUT size is usually not too bad. You're going to see later on that there's fracturable LUTs. Fracturable LUTs are actually a lot harder. Okay, they changed the software more, so the cost of doing that was higher. I don't know if that answers your question or not.
I guess, yeah, in a sense, it's just that it seems to me like it's been, Western microchips also, for a while, stuff like 4 electric designs out there, and stuff like 6 electric.
Yeah.
Like, it seems to me there's probably room for ability across process nodes and just like sticking with 6 nodes for
Yeah, they change other things. So they're changing how their logic blocks work and how their routing is constructed and how their arithmetic works. But you're right, the LUT structures themselves, they kind of went 4 LUT for a long time, then fracturable 6 LUT, and then it tweaks exactly how that works, but nobody's gone to a 7 LUT. There is some divergence of like, Microchip, for example, I believe uses a structure with 2 4 LUTs cascaded together, or certainly they publish papers on that, right? So I think, and there are academic papers where they take out, there's one at FPL where they took out the last part of the LUT and replaced it with some AND gates and muxes and say that it works better. And their data seems reasonably convincing. So I guess the LUT is granular enough that there's only so many choices that make sense, right? Like 4, 5, 6 look pretty good. 7 looks too big, 3 looks too small. So I don't know, so there's only so much design space to explore there, right? And then there is how might you combine those in the logic block, and that gets changed more often, I think. Does that make sense? Okay, so we're going to look at how we pick this best LUT size. So that's this is one of the questions we want to get some insight into. Okay, then also, should we combine these LUTs into a logic cluster? So that gives us this 2-level hierarchy, BLEs and then a logic cluster. It helps the CAD tools, or it can help the CAD tools, because we can choose if we want to cluster into this larger block, and that can simplify some aspects of the CAD problem. We already talked about this on the whiteboard, but it allows some word-wide signals. This is a natural way to say, within this logic block, you all share the same clock. Maybe you all share the same clock enable, the same asynchronous clear, the same synchronous clear, the same S load. Because usually, I mean, if you have a design and you use a different clock enable on every single register, a different clear on every single register, and the worst of all, a different clock on every single register, I mean, you are in like lab 2 of 241, and it's not going well, right? Like, you're...
You joke, but they do that.
So this, in disciplined designs, these usually have, the clocks usually have quite high fan out, right? At least most of them. And these signals have pretty high fan out too. So they make sense to group together in a physical structure where you don't need so many muxes, et cetera. You're sort of a broadcast within the logic block. Okay, but if we so first question is this a good idea? Then if it is, how many things should we put in it? What's this best number of BLEs? How many inputs should we take in, and how much interconnect should we put in the cluster? Okay, so how do we answer that? You basically can't answer it on a whiteboard. It's too many trade-offs, so you can get some insight. So you have to do it empirically. So Dave Lewis, who you'll see his name on lots of the Altera papers, he's Altera's kind of chief FPGA architect on many generations. If you didn't do this, right, you just said, I'm sure this is better, he called that architecture by vigorous assertion, right? How vigorously can you assert this with no evidence whatsoever? He did not say that as like a good practice, okay? So when he said you were doing that, he was telling you, you need to go do this, okay? So you find benchmark circuits that you believe are representative of what you're trying to do. You build a parameterized compiler or CAD tool, right? So this is a CAD tool, but it effectively is a form of compiler. that map circuits to the architecture. You estimate the area and or delay and or power. Nowadays you do all three of those, and you get estimates of architecture efficiency. And you'll try this for a whole bunch of different architectures, and you don't want to do it for one circuit, you want to do it for a whole bunch and kind of average results or take the worst case results. Usually you average them. Okay, so that was pretty high level. So what should I use for my CAD flow? So I could optimize gates. Berkeley has a nice synthesis tool called ABC, so I could use that. I could technology, so I could take my benchmark circuits, maybe they're in basic gates, I optimize them. I technology map, which means I map to what's actually on the chip, so I need to take these gates and map them into LUTs, which is a kind of a form of bin packing problem. And at that point I could say, okay, my area is, let's count up how many LUTs I used on a benchmark, multiply it by my area per LUT, and my delay is take the depth of the circuit. That's basically how many of these LUTs are in series on the longest path between two registers. That's the depth. Multiply that by the delay of a LUT, and I've got my delay. Okay, so I do this. I write my paper. I submit it. What do you think? Is it good? Bad? Everybody wants to review this paper. So, Amir, what do you think?
The only thing it evaluates is like the internal structure of the DLE, but like anything outside of that is.
Yeah, so you're not nuts about this, okay? Adam, what do you think? You're going to give me the positive review that I need?
Because, like, for example, if you're going to technology map, like looking at stem cell injuries, there's always some report on like the worst case input, the worst case output. So that's one thing that you're not really considering looking on the picture. And if it's an output to match, right? That's into the wider concern is not taking into account routing.
Yeah, so I think both of you said essentially similar things. So you're like, you're only looking at the internals. You're saying you're not looking at the routing. That's going to mess up your delay. Also going to mess up my area. So this is not good. Should never be rude in a review, but you write a review that says, you know, this paper does the following, just does it quite poorly. Better luck next time. So yeah, Alex.
A reviewer 3 didn't read the paper and asked for more benchmarks.
So, yes, this is bad. And the reason is it's ignoring routing, okay? Which sounds, you know that's really bad, but there are papers that just do this because it's easier, right? Routing is kind of hard. You're like, how much routing do I need? What's the delay? You need actually a pretty complete CAD flow to do that. This CAD flow is not trivial, but it is actually a lot easier to get these parameters and build this much of a CAD flow. So maybe you have some new logic structure and you put a bunch of work into making a new technology mapper. It's still not enough, right? You need something that handles routing. So there, you could make it better without too much more effort. So even if you say I can't build a full CAD flow, I'm going to stop after I technology map to these lookup tables. You could say, well, my area is the area of the LUT, but I also know that I've got k things to hook up to the general routing. So we'll say k times the number of ports per LUT, and my area of an output port, I'll multiply that by n LUT. Okay, these are actually going to be kind of hard to estimate because I'm going to have to guess a routing architecture that works, but at least I put a guess in, right? A guess is better than zero. And at least I understand that if I add more inputs to my LUT, this k is going to go up, and that's going to drive my routing area up too. And my delay, I can say it's the delay of the LUT plus the delay of the routing. I don't have a very good way to calculate this either, but again, at least I can make a guess, and I can say how I made my guess, which is better than implicitly guessing zero. So better, but if you want to do better than that, you need to build a full CAD flow. So what's common is building a full CAD flow is a lot of work. Okay, so usually what people will do is they will try to augment some CAD flow so they can answer their one question. And the most common CAD flow that they'll augment is this VPR/VTR. VPR is kind of the place and route engine and the main part of this VTR flow, so they kind of mean almost the same thing. One is like a component, the other is the whole thing. It's basically the same flow as we talked about. You have benchmark circuits, so you got to get a bunch of different designs that you think are reasonably large, or they're in the right size range, they are in the right application domain, etc. Or maybe it's a very general FPGA, you need to cover multiple application domains. So there are some published ones you can use. If you're a company, you're gathering these all the time from your customers. When I was at Altera, every time Quartus crashed for a major customer, we'd ask for the design so we could fix the bug. We'd also keep the design as with their permission, right? But we basically, if they didn't explicitly kind of tell us we couldn't keep the design for benchmarking, we would use it for benchmarking. Okay, so we did send that. They're generally at the HDL level. So in this flow, you go into a tool called Yosys, which is basically an open source synthesis tool. It includes inside of it ABC, which is the Berkeley tool that can do optimize gates and do technology mapping to LUTs. And it has a plugin called Parmis that understands basically this architecture description. So it understands the hard blocks, and it tries to use the hard blocks. So the combination of this, you can retarget your synthesis engine by changing this architecture description, okay? And yeah, I kind of, ABC calls, or Yosys calls ABC. So Yosys really is about taking HDL and turning it into gates, and then it calls ABC to optimize them and technology map the primitives, and it calls Parmis to say, what do I do about hard blocks? So that's kind of how that whole synthesis flow works. Then everything I've shown in like this cyan color is the VPR component. So it basically has a description of the architecture, and that description also includes delay numbers and data that's needed to estimate area, layout area. So that implicitly means that it also has knowledge of, you have to have knowledge of how the circuits are built and the process in order to give it all that information. It then takes, so this is human readable. It's XML. For a complicated chip, this could be pretty big. For a not complicated chip, it might be 200 lines of XML. For a really complicated chip, it might be thousands. But it's still human readable. Inside VPR is an architecture generator. So what the architecture generator does is it takes this human readable description and basically turns it into the really large data structures, like basically a grid of where can everything go. So, and a big graph that describes all of the wires and switches. So those are two of the fundamental data structures that are much bigger. So this is like hundreds to thousands of lines. After you go through this architecture generator, you have basically an in-memory database that is, again, basically two-dimensional grids and big graphs. And those things are now, for a big FPGA, gigabytes to tens of gigabytes. So what this architecture generator does is it makes you productive, right? You probably don't want to be generating those gigabyte to 10 gigabyte files by hand for every architecture. So instead you specify, these are the key things I want, automatically build those data structures. And sometimes some aspects of this architecture description, you can leave things a little bit vague, and the architecture generator will essentially, for example, if you say, make me some reasonable switch patterns, but I want these lengths of wires, the architecture generator knows how to do that. So you can essentially make your specification a little more vague, and there's enough intelligence in here that it should make you a reasonable architecture. If you know exactly what you want, you can make it more detailed, and you'll control this more. Okay, so this architecture database, like this in-memory representation, some of it goes to synthesis. It needs a little bit of information. What's the LUT size? What are the hard blocks? That kind of thing. More goes to what's called the packing step, which basically takes these LUTs and flip-flops and a few other things like little bits of adders and puts them together into logic blocks. And also takes little bits of RAM and puts them together into RAM blocks, and can take multipliers and put them in DSP blocks. So that's called packing. It's basically like assembling that first level of the hierarchy, right? Take these little things that came out of synthesis that are called primitives, pack them together into these clusters. After that, we place them. Okay, so we put everything in a legal spot. RAM goes in a RAM spot, DSP goes in a DSP spot. Try to optimize the amount of wiring, try to optimize the speed. Then we route it. Okay, so you choose non-overlapping paths for all the signals in your design, going through this big graph that represents all the wires and all the switches in the chip. All of these are timing driven. So synthesis isn't timing driven in this flow. Okay, so notice there's no arrow here. Timing driven means that you can estimate delays for all the different parts of your circuit. You can send them over to a timing engine, and you can say, tell me what the slack is, and give me an estimate. Well, you can get essentially a slack on every single connection in your design. So not only do you get how fast is this design overall, if my guesses for delay are correct, but you can also see how much slack do I have in every connection. And that allows you to see, well, you have almost no slack, right? So I need to really prioritize. Try to like change the placement and get this connection shorter. This other one has a lot of slack, I don't really care about it, right? I care about it for wiring, but not for timing. So each of these algorithms are talking to the timing analyzer many times. So placement and routing usually will talk to it like 50 to 100 times as they gradually optimize. Packing doesn't, just talks to it a little bit, once or twice, and synthesis not at all. This is actually pretty similar to what Cordis does as well. So the reason for this is that up here, when you're doing like these earlier optimizations, that your delay estimates are so crude that you can effectively just say, just assume that you can optimize logic depth, right? If you just optimize logic depth, it's pretty close, because if you try to guess delays, your estimates are bad enough that it doesn't help you very much. So you can get a little bit by hooking this up to a timing analyzer, but less. As you get further in the implementation, the gains from hooking up to a timing analyzer and repeatedly asking, how am I doing, increase. So then the last stage of this is basically something that you wouldn't have in like a Cordis or Vivado. It's basically now go estimate what does this FPGA cost. So it essentially builds the low-level circuitry. Using these models you gave it, it says, well, how much layout area do I think this chip would take? And estimate the area, the delay, and the power. Okay, so that build the circuitry step is different because it's kind of doing it automatically, whereas Cordis, that's like an input. Like the chip has been built, it's all just been measured. Here we want to do essentially virtual prototyping. Okay, then you get area, delay, and power numbers, and you decide if your architecture is any good, and you'll usually go back and change this. So you will do this, you will run maybe 100 benchmark circuits through and average them if you're in industry, and you might look at 1,000 different architectures. Some of them might be wildly different. Those are a lot of work to model. Some of them might be small differences, and those are much less work. But you'll generally look at a lot of different options before you commit to, this is what I'm going to do for the next generation. Okay, so we're using this flow. You will actually use this flow for your assignment 4. You won't have to write any of it. This is common that you go, I don't want to write this whole tool, right? This whole tool is 1 million lines of code, so that would be a really hard lab. So instead you run it and you do some architecture experiments, and that's what most academics do. They might make a change here or there. A cousin of this flow is Altera's FPGA modeling toolkit. So they have a closed source version of VPR that they use in basically the same way, right? So this is also, a cousin of this is also used in at least one major player in the industry. And I think other companies have their own versions that will be different code bases, but the similar idea. Yeah, sorry.
You said like a company would try like thousands of different.
I mean, it depends how much money they have. Okay, so Altera, we would try thousands. If you were like, this is Dave Lewis' term too. He would say Fred in the shed, right? So you're Fred in the shed, you're like a very small company making an embedded FPGA. You might try 5. Do you know what I mean? Because you don't have the time or the money for 1,000. So
But like the variation between one.
some of those are going to be pretty small, right? Like, so if you did 1,000 radically different ones, then you better have an awful lot of money. So let's take the Stratix 2 paper that you're hopefully reading. So some of the big differences there would be like 4-LUT, 5-LUT, 6-LUT, a bunch of different variations on 5 and 6-LUT, fracturability, how populated is the crossbar is another big one, and what does the switch pattern look like? And then changing the wire lengths, permuting the switch patterns, and some of those like, okay, let's put a few more of this kind of wire in. Okay, let's put a few more switches in, let's take a few switches out. So some of those ones like, let's change the logic cluster size, right? Instead of like 10 DLEs, let's put in 8, let's put in 12. So some of those are pretty easy. Like you literally might be changing like 1 or 2 lines in like the architecture file and then burning a bunch of compute. Some of them might be pretty hard, right? Like you're changing a bunch of things and it takes a while. Yeah.
This flow I see has a lot of like biases that are good bias, because we want to model those things, but.
Could be good bias. I might also have bad benchmarks.
Right.
And usually, even in, okay, so in academics, they usually get benchmark suites. And there's concerns of, is your benchmark suite up to date enough?
Right.
So that's why once in a while, some group will go off and make a new benchmark suite to try to improve that situation. It's also an issue in industry. Like I told you how in Altera, we would gather these designs from customers, our own IP groups would make them. And we'd never have as many as we wanted, as big as we wanted on the latest applications. When you're building it, you're trying to build the next generation chip, you're kind of like, well, this is all built for designs that are twice as big as what we could do right now. How many designs do we have that are twice as big as what we can do now and are targeting the next generation I/O standard or wireless standard? Well, often zero, right? So you'd have to go, okay, let's scale some of them up. Maybe we'll try to make one, and then we're going to have other ones that are older designs, hopefully not too old, but it's imperfect.
There's also bias in the pack place and wrap, for example. It was designed for an architecture, now we're changing it to an architecture it's never seen before.
Yeah,
So is there any way we can prevent that kind of bias?
that's a good question. So not really.
Gotcha.
So basically, if your CAD tools don't optimize equally well for all architectures, and they generally don't, then your results are biased. You might have better architectures that you don't go and do. You try to fight that by making these algorithms quite adaptable. And if you change the architecture radically, you have to spend a bunch of time on the CAD tools. You have to expect that the CAD tools will be quite inferior for a while. You got to go look at it, try to improve what they're doing, which does make those radical changes a lot more expensive to evaluate. So, and you're never sure, right? So you try to, so a lot of FPGA manufacturers, what they'll do is they use their production tools. Right. And they'll make small architecture changes by, so Quartus or Vivado, for example, would be production tools. And you make small changes in the production tools and try to evaluate it. You have high confidence for small changes because you go, we've been beating on this tool for like 10 years. It's really optimized. But you usually have low confidence or it's impossible if you make a radical change because it's just too much work. A parameterized flow like this instead generally gives up some optimization quality because it's adapting to the architecture. Its goal is to basically be more fair to a wider range of architectures, but that's never infinite and it's never perfectly fair. So, at Altera we would do both. We would primarily use this parameterized CAD tool, like the closed source version of this, to evaluate the architecture until we got close, and then we would do some final experiments in VPR that were really fine-tuning, and then maybe some final ones in Quartus, which were much more expensive because now you're pretty close. You're actually making a lot of code changes, but you're fairly confident that you're going to actually put something close to this in the next generation. So hopefully it's not all throwaway. So you can do both, right? Search the broad space with more parameterized tools, and then take some highly optimized, more specific tools to kind of validate them in the last couple points. Okay, so I'm going to talk about a classic paper here. It's done by Jonathan Rose, one of his grad students here at U of T. So they looked at basically what should we use for LUT size and cluster size. So the first question I put up there. Okay, so let's go through that. So the first thing they looked at is, well, maybe we should just use a single LUT. Okay, so they use this BLE where they had a LUT. This is a 4 LUT. They're using the style where you can have a register. You can use either the registered output or not, right? The combinational output. And what I'm showing here is they averaged over 28 benchmark circuits that layout or the process independent or kind of process independent area metric, the minimum width transistor area metric that we talked about last week. Okay, so they're averaging it over all these benchmarks. And what this solid line is showing is area per cluster. And their cluster is really small. It's just a single LUT. And as they go from 2 LUTs to 7 LUTs, the area grows really fast. So it starts going exponential. Okay, and we already knew that was going to happen. But the number of lookup tables that they need is this dotted line, again, averaged across the whole benchmark suite. And it's going down pretty quickly, actually. So if they use like 2 LUTs, they needed about 1,600 LUTs for the average circuit. And if they use 7 LUTs, they're down to maybe like, actually this is a number. So no, they went from like 4,500 down to like maybe 1,400. So it dropped quite a bit. But their area has gone from 100 of these minimum width transistor units to like 1,600. Okay, so the LUT's gotten a lot bigger, but you need fewer of them. Yeah.
The way that the scrap's sort of laid out, does it mindlessly try to look at that intersection point at some sort of best case, or not best case, but I have a nicely balanced point?
It does kind of point you that way. I don't know if that was on purpose by them or not. I mean, to be honest, you could argue it's a bit misleading. This doesn't go down to zero, right? So really, this axis, like, it is visually a little bit misleading, right? But too late to review this now, right? It's classic paper is not getting changed. Okay, so, but I don't know what the best point is. Maybe it is just the intersection point, so maybe it'll all work out. But I got to put these together. Okay, and this next slide does put them together. So this is the total FPGA area. So we just multiply the number of blocks that we needed times the area per block, including the routing, okay? And so this is now not just a LUT, it's including the routing, so it's got all those effects in it. And they get a pretty broad minimum. So actually anything from about 4 inputs to 6 is pretty close to a tie. So in what they did here. Okay, so that was a very small logic block though. It was a single lookup table. So the next thing to look at is, well, maybe that's not the best logic block, right? Maybe we should use these logic clusters, right? So let's group n of these LUTs and flip-flops together with some local routing. The local routing they use is a full crossbar. So that basically just muxes. You can build full crossbars out of muxes. I've got n outputs for n BLEs, because each of them can send out either their combinational or registered output. And I've got some number I of inputs coming in from the general routing. So yeah, this is my hierarchy. I've got this basic logic element, which is a KLUT and a flip-flop. I put n of those together with some local routing to make my logic cluster. And then I tile those out into an island-style FPGA. Okay, so kind of 2 levels of hierarchy inside these tiles, and then I spatially repeat the tiles to make this island-style FPGA. And what they looked at is basically how do area delay and area delay product, which is basically, if you minimize area delay product, you maximize throughput, right? Because you could put more units in if it's smaller. You could clock them faster if the delay is lower. So area delay product is like 1 over throughput. So if you're going to pick one metric to optimize for, this would be it, right? In order to do a study like this, you have to decide, like they want to take routing delays and routing areas into consideration, so they have to pick a routing architecture. So they picked a simple one, but a reasonable one. All the routing wires are length 4. Other research has shown that's a pretty reasonable length. If you picked one routing wire length, that's a pretty good one. It might change from one process to another, but in this process is a good choice. They use a full crossbar. So this local interconnect is a full crossbar from the logic cluster inputs to the BLE inputs. They have to choose how to electrically build the wiring. So they didn't use muxes in the routing switches. That actually was found after this paper, some years later, to be a better idea. So what they used was a mix of tri-state buffers, and we'll talk about routing architecture later in the course, and pass transistors. It's a reasonable routing architecture, but doesn't match exactly what people would do now. So maybe that influences their answers. And it is also done at 180 nanometers. So it's done in a much older process than we have now with a significantly different mix of wire and transistor delays. So there's some reasons why people have actually repeated this study with later CAD tools and process parameters. It still gives the right overall conclusions, but the exact details will be different if you go to a different process and different routing architecture. Yeah?
When they estimate area and delay, what actually are they estimating? Is that like the tile area, or and what is delay, the critical path delay?
So delay is the critical path delay. They'll get that for each circuit. And it's based on essentially spicing. You design this low-level circuitry, like the actual routing muxes and the routing wires and the LUTs and so on. You spice them to get estimates of their delay. You put those all in the architecture file, and then VPR will add up. They use VPR for the study. VPR will add up all the delays on the critical path and tell you this is your speed limiting path. Okay, so that's delay. Area, it's basically that minimum width. This is inside VPR, it knows how to build essentially transistor level circuitry, just for the purpose of area estimation. So it basically is like, how many switches did you ask me to build? How many SRAM cells is that? What drive strength did you say they are? And it'll build all of that stuff, and then basically tell you this is how much area in these minimum width transistors your FPGA takes. So you can use that to compare one A to B. Does that make sense? Okay, so when you go to these logic clusters, you've got a little more circuitry to think about in the logic block. Okay, so we've got this basic logic element here. So we've got a K-LUT and a flip-flop, so you've seen that over and over again. So each of those has a delay in the architecture file. We also have the ability to feed the output of these BLEs back into the local routing. So this is my local routing, okay? And it's a full crossbar. It basically gets I inputs over here from the main routing, and it gets N inputs from these feedback connections, right? The outputs of things that are in the same cluster. So every MUX here has N plus I inputs, and we need K times N of them. So it knows inside their paper, they're basically building these MUXes when they're estimating delay in area. So as the cluster gets bigger, there'll be more of these MUXes, and they will get bigger. That will increase their area. Also, the delay of each one of these MUXes is going to increase. And these wires are going to get longer, so their delay is going to increase. If I have to go out of the cluster, I basically have a buffer, so an output driver after my LUT or flip-flop, and I drive onto routing wires with these pass transistor switches. And on the other side, from the routing wires, I have a MUX, just like the one we drew the other day, to select which routing wire feeds into every one of these I inputs for the cluster. Okay, so they have delays that they have to get for all of these things as N and I and K varies. They have a whole bunch of spicing to do and a bunch of calculations of areas. Yeah?
Why don't they have like the output where they go to the routing segments? Why do they not have the buffers after transistors? Because like the wires have significant capacitance.
So nowadays what you would do, we'll read a paper about something called direct drive routing. So it's actually better, and let me think about that. In direct drive routing, you would actually you basically change this to MUXes, okay? And you actually would have all of your MUXing done with pass transistors on this side of the buffer, okay? So it's a good idea. We're going to get to a paper that shows that's a good idea. That wasn't known to be a good idea at that time, okay? So basically, it built a big buffer here and then big pass transistors, because this is capacitive. So these are not small pass transistors. They're large, because you're right. This has a lot of capacitance. These have to be sizable. So good question. There actually are improvements in routing architecture since this date. So you probably wouldn't build it that way now, right? There are better ways that are known to build, and there's a paper called direct drive routing that basically lays out that trade-off. It was one of the papers that kind of showed this was a better way to do it. So good question. Any other questions on this? Okay, so let me keep going. Okay, so first thing that they do in this paper is they go, well, like we got a lot of parameters here. We got to find a way to start setting some of them. So the first one is they said, we know we want to sweep this number of LUTs per cluster, N. But in order to do that, we need to decide how many inputs we build per cluster. And we don't really want to do like all possible inputs with all possible number of LUTs. So what they did instead is I think I did this and they used this result, but whatever. Same idea. They basically took the packer and they said, how many inputs do we have to give you for you to pack the clusters very full, like 98% full? And I did that, and I basically just arbitrarily decided 98% seemed pretty good. So as we basically go up in cluster size, like number of LUTs, we need more inputs. That makes sense. And what this paper found, which they rely on, is that the number of inputs you need is basically about half, right? So I have actually kn LUT inputs if I have n k LUTs. And this paper showed that you could actually pack logic blocks pretty much to capacity if you built about half that many inputs coming in from the general routing. So the reason you could do that is the packer can find and should find LUTs that share inputs, right? So they have something in common, or LUTs that feed each other. And it's pretty good at finding that, so it actually only needs half the inputs that it would need if all these LUTs were unrelated. And you really don't want it putting unrelated LUTs together, because that's going to increase the number of inputs you need per logic cluster. Is from the equation we saw last week, lambda r bar, the wire channel width. Whoops, let me not do that. All right, let's see if I can get this back. Okay, remember we said lambda r bar over 2 was an estimate of the average channel width, and lambda was how many inputs I have to a block, right? The average number of inputs. So I really don't want to have too many inputs to my average block. It's too many signals getting dragged across my chip. I need more routing. So your packer wants to put things together that share signals or feed each other. And if you give it a constraint of, you say, well, you can't, like the most inputs you have is this number I, and it's about half the total LUT inputs, it's okay. It actually can, that's what this black line is showing, that it can pack the logic blocks full. And the average number of inputs grows even more slowly. So this k over 2 is still linear, though, in the amount of logic I put in, right? So I put n things in, I need a certain number of inputs. So I put 2n things in, I need twice as many inputs. So what rent exponent would that imply? So I put twice as much stuff in, I need twice as many inputs. What rent exponent gives me that? It's not a complicated exponent. 1, yeah. So while the packer is clearly able to grab some related logic, it could probably do a bit better than this. And we can see that the curve is kind of flattening out, so it's maybe a little less than linear. But the other thing is the average inputs. Rensrow predicts the average inputs, not the worst case. Okay, so if I look at this average inputs, it's somewhat more sublinear. So the rent exponent is worse or is better. This also might mean there's some room for improvement in the packer they were using, right? Because in typical circuits, you should find a rent exponent that's maybe more in the 0.5 to 0.7 range. So this looks a little high. So maybe there's some room for improvement in the packer. Okay, so then they do a whole bunch of charts that I'm going to try to walk you through on how do these parameters n and k affect area. So they've kind of set I to be about half the LUT inputs can come into the logic block. And what they're doing in this chart is they're showing how much area is in the logic cluster. So that's why I circled this. And on the x-axis is what's happening with LUT size. So we're going from very small LUTs to very big LUTs. And on the y-axis, this is a cluster of size 1, and then a cluster of size 2, and so on. This is a cluster of size 10. So it kind of makes sense, right? This is just the area in the cluster added up over the whole design. Let's take all these designs, add up all the area inside the clusters, average it. If you use bigger LUTs or bigger clusters, that area goes up. So it's not shocking. Goes up faster with LUT size than with cluster size, but it goes up with both. But then if they look at what about all the area outside the clusters, all the routing we need to hook them together, what happens to them? And they do it on the same axes, right? So LUT size going up, and this is a really small logic cluster, cluster size 1, and my really big ones are down in here, okay? So here we get the exact opposite trend, right? as we go to bigger LUTs and bigger clusters, all the routing area outside is smaller because just fewer signals go out there. We don't need as many clusters. Each cluster has more inputs and outputs, but when we add it all up, there's just fewer signals that need to go between clusters because we captured more. So our routing area goes down. So we have to put those two together to figure out what's the overall impact on area. And they find kind of a broad minimum. Okay, so for LUT size, the best is around here, 4 to 5. And the cluster size is increasing as we go this way. Okay, so bigger clusters are actually helping reduce area. So they're good. And the cluster size 1 is here. Okay, so cluster size 1 is not as good as these more interesting logic blocks that actually have local routing and a bunch of things in them. So logic clusters are a good idea. And if we go into the larger logic clusters, so those were kind of the smaller ones, from 1 to 5 LUTs. We go into the bigger ones, we get kind of a broad minimum. The absolute best architectures are here at a LUT size of 4 and pretty big cluster sizes of somewhere around 7, 8, 9. So anyways, we get a pretty broad minimum. LUT sizes of 4 is probably the best. 5 is reasonable, and you want reasonably large clusters. These trends aren't obvious, right? Like you have these competing trends. Like there's a lot of complicated things happening here, right? So you really can't predict this without a CAD flow. Okay, what happens on speed? So on speed, as we go to bigger LUTs, this is basically our critical path delay, averaged across all these benchmarks. So smaller is better. So as we go to bigger LUT sizes, speed is getting better. And that never really stops. So we're getting maybe less gain as we go to really big ones, but we're still getting some gain. And larger clusters are also good for speed. So this is like a cluster size 10 here. This is a cluster size 1. So cluster size, the local interconnect is actually helping us a lot. Like going from a cluster of size 1 to 10, it's actually quite a lot faster. And it is basically because we've captured a bunch of connectivity on this local interconnect, and it's fast. So that first level of hierarchy is helping us. It's a bit faster than what we were building with just we went straight up to the island style routing. Okay, so again, if we want to pick one thing to optimize in an FPGA, you'd pick area delay product. So if we do that, we find there's again a broad minimum. Okay, so now anything between 4 and 6 lookup tables looks pretty good. And we want reasonably large clusters, anything from like 4 to 10. But we've got a pretty broad minimum at this point. And all of those, the ones over here at LUT size of 6 are faster but bigger. The ones over here at a LUT size of 4 are slower but smaller. But they both have similar area delay product. Okay, so that's kind of the summary, right? So a bigger LUT, capture more logic, fewer levels of the critical path. The LUT itself is slower, slows down linearly as you increase inputs because you get more levels in the muxing inside the LUT. Cluster size, so N, bigger basically reduces your demand for general routing. It captures more connections on this fast local routing. But its area grows quickly as N squared with a full crossbar. I mean, it's an N squared for the local interconnect. For the first while, that's not too bad, but eventually it starts to dominate. So this puts a limit on how big you can make N. If you don't use a full crossbar, you can kind of reduce the constant in front of this, maybe even make it less than N squared, so you could push it a bit further. But in the study I just showed you, they use a full crossbar. The local routing also gets slower as you make the logic cluster bigger. So you're able to capture more connections on it, but the gain for each connection gets a bit smaller. The delay slows down roughly linearly with N. Okay, so the area is going up quadratically because you've got more muxes and each one's bigger. The delay is going up linearly because you just get bigger muxes and longer wires. So hopefully that makes sense. Yeah, and there's basically a summary is that big LUTs are good for delay. Large clusters are good for delay. area, 4-lets are still best, kind of reasonably large but not gigantic clusters, like size 6 to 10. And the best area delay products, you get a large minimum from 4 to 6 LUT size, cluster size of about 4 to 10. And the 6 LUTs faster, but it's bigger. Okay, so while 6-LUT and 4-LUT, their best architectures are close here, they're close in different ways, right, in terms of what optimizes delay versus area. Yeah?
So building off of Adam's question as to why like Chorus and Altera and Xilinx have gone to 6 LUTs and someone like Microchip might stick with 4 LUTs, could that be a revealing of kind of like what their value proposition is trying to be for their customers?
Partly.
Altera and Xilinx want to be faster while someone else wants to be reducing area. I know Microchip always wanted to be sort of like better on power. Better on power, so that would reduce area.
Power does to first order correlate with area. Yeah, so if you care more about power, then the fact that the 4-LUT is more area efficient is more compelling to you. Also so that's one reason. The other reason, it is interesting, like how often should you revisit these things? This conclusion, I'm going to show you now an industrial paper that came to a similar conclusion, but looks at these more complicated fractional LUTs. So I guess with just this trade-off of 6 LUTs versus 4 LUTs, if you care more about area, you should do a 4-LUT. If you care more about delay, you should do a 6-LUT. The exact trade-off will change, though, as you change your routing structures, you change your process technology, and so on. So you also shouldn't take this as venture capitalists just gave me $50 million. I spend $49 million at Vegas, and I read this paper. Probably not the best idea, right? So Microchip also has some there are other ways you can try to get speed. So Microchip cascades, I believe, they're 4 LUTs together. It's another structure that can get some extra speed out of a 4-LUT. And it wasn't evaluated in this paper, so we just can't locate it on this chart. Let's see. Okay, so let's talk about fractional LUTs. Let's see. Okay, let's go through this and then we'll take a break. Okay. So we had a trade-off there, right? 4 LUTs, smaller, 6 LUTs, faster. And Stratix 2 was the first architecture that looked at this thing called fractional LUTs. That has now become like very common across at least high-performance FPGAs. And I guess I just said that. Okay. So this is results from Altera's internal CAD flow. So that basically their internal version of that VPR CAD flow I showed you, run at the time of Stratix 2. Okay. So what is this showing? It's basically showing averaged over a whole bunch of benchmarks. How many inputs do we use in each lookup table? And you have to tell the synthesis flow in an FPGA CAD tool. I already kind of showed it to you, but it basically, the first part looks a lot like ASICs, right? Recognize what the HDL means. That's called elaboration. So you turn things into basic structures. Optimize the gates. So that just means like you might figure out, oh, I could turn these 2 AND gates into an OR gate. That's better. Okay, so that looks also like ASICs. The next step is called technology mapping. That's different. Okay, you map to lookup tables. So you kind of like a bin packing problem. This is showing the output of that tech mapping step. So we stop the CAD flow after that point and we measure what have we got. So we have to tell the technology mapping step how many inputs are there in our LUT. So we could say we're doing a 4-LUT or a 5-LUT or a 6-LUT. So the blue bars here is Altera told the CAD tool you have a 4-LUT. And so you would hope that, well, everybody uses 4 inputs because you built 4 inputs. That 4th input was quite expensive, right? Going from 3 inputs to 4 inputs is like twice the area, so I want you to use that 4th input. But it only used it about 55% of the time. It used 3 inputs about 25% of the time, 2 inputs 11%, and 1 input like 8%. So what are you doing with this 1 input LUT, by the way? This still surprises me, actually. Every time I show this, I'm like, what are these 1 LUTs? What do you think they're doing? Yeah, it's a NOT gate, or it's a buffer, right? It's even more useless. So you go, what is this doing? So it does look a bit crazy. You do get some NOT gates. This looks super surprising until later in this lecture I'll talk about arithmetic. So sometimes when you have so you might have registers feeding each other. Okay, like I just got a shift register, so this register to that register. The synthesis tool might put a NOT gate in there. Maybe it doesn't. Or more commonly, when you get things like arithmetic, you might just not be able to use the LUT. It's just acting as a feed through to get to a structure that can do arithmetic. So there are reasons why this happens, although it still looks a little surprising. And I'm giving you kind of plausible reasons, because I think this is, otherwise you kind of go on the synthesis team needed to work harder. But anyway, we're not using the 4 LUT to its full capabilities. Okay, what if we do 5 LUTs? Okay, because we know that'll be a bit faster. It gets worse. Okay, so only 40-something% of the LUTs actually use 5 inputs, and the rest use 4 or fewer. And if we build 6 LUTs, only like 35% were using all 6 inputs. Why don't you use all 6 inputs? So there's lots of reasons. Like if I had to, basically use a LUT to get to a carry chain, maybe I couldn't find anything to put in front of it. So that might give me like a 1-input function. I might have just only a little bit of logic between my registers. So there's just not enough to fill a 6 LUT. I wish there was, but it's just not there. I have a big cloud of logic, and it turns out when I start covering it with LUTs that some of them just aren't 6 LUTs, right? So all those things happen. So there's a bunch of reasons why you don't get to use all those things. Yeah?
I think you ended with that, but it's like basically like whatever function you have in your rectangle or whatever, it just doesn't end up being
Yeah, so you can take even a big cloud of logic and you can go, it turns out that you can cover this with like 3 6 LUTs and like 1 4 LUT, and that's just the way it is, right? That by itself, if everything was a big cloud, I wouldn't expect it to be enough to result in this, but then you also do get a lot of pipelining where you kind of cut things up. And from the tech mapper's from the speed point of view, that's a very good thing. From the tech mapper's point of view, it's probably very annoying. It likes to go find lots of gates that'll fit in a LUT, and it's finding some good gates, putting them in, filling the LUT up, and then it hits some registers. And there's just registers everywhere. And it's like, okay, I give up, I stop filling that 6 LUT. There's nothing else to put in, okay? If everything you had was like that, then you would just say don't build a 6 LUT. But you do wind up with these clouds of logic with many more inputs, and they can limit your speed. So you kind of you'd like to be able to use your 6 LUT there. Okay, so the idea was kind of motivated by this, right? Like when we build 6 LUTs, we use lots of them as 5 LUTs and 4 LUTs, but we just kind of waste all that extra circuitry. Like when you use a 6 LUT as a 4 LUT, you basically use 1/4 of its SRAM. You got all this other SRAM and this big mux tree, and you're using basically 1/4 of it. So it feels a bit wasteful. So the fracturable LUT idea is take a big LUT and be able to decompose it into 2 smaller LUTs to make these larger LUTs essentially more efficient. So we can use it as a 6 LUT when that turns out to be a good idea. Sometimes it's a good idea just for area. It turns out it captures a ton of logic. Often it's a good idea for delay. It just grabs, you get fewer things in the critical path. But basically when we don't want to use it as a big 6 LUT, we want to be able to efficiently make 2 smaller LUTs. Okay, so the first idea, yeah.
I guess that wasn't entirely clear to me from reading the paper, but could you, because the idea is like you decompose into 2 smaller, you then decompose those 2 smaller LUTs into each one into another set of 2 smaller.
Yeah, no, you could. So you could take the fracturability further. It's kind of a fractal pattern. And there are some papers that there's actually some papers that I wrote with Andrew Boutros, for example, where we did that for arithmetic. You kind of decompose the LUTs more in order to be really good at certain functions like multiplication, right? So.
But I guess for the strikes, it was only
We only decomposed into 2 for most things. When we get to arithmetic, you'll see there's kind of a little more decomposition going on. And that is a valid thing to do. You could decompose more. The thing you're weighing against is I guess you'll see it in the next few slides. Basically, there are some costs to decomposition, right? So you get to reuse a bunch of circuitry, but you do have to add some stuff. So then you do have some cost, and so you want to be able to make sure you use it enough. But that's certainly a valid place to go. There are reasonable things you could do there. Okay, so here's the first 6 LUT option. Okay, so what the paper calls a composable LUT. Okay, so the key thing to realize is that to make a big LUT, like a 6 LUT, you have to make small LUTs first. So I've got 4 input lookup tables here. So 16 SRAM cells and a 4-level mux. And I do that 4 times. And then I basically combine the output of these 2 LUTs with a mux. So that's actually a 5 LUT, right? I have another input that comes in, selects that. That actually is a 5 LUT. do it down here as well. And then I've got a sixth input that comes in and runs this last stage of muxing, makes my sixth LUT. So if I only had this output, then this would just be a regular 6 LUT. But I actually bring out other outputs. I'm going to bring out this 5 LUT output. I'm going to bring out this 5 LUT output. I'm going to bring out each 4 LUT output. I'm going to basically give each of these 4 LUTs their own inputs. And then I'm going to give each 5 LUT its own 5th input and the 6th LUT its own input. So I have lots of flexibility, right? I can build 4 LUTs. I can build 2 5 LUTs. I can build 1 6 LUT. They all work fine, basically without restriction. So do you love it?
So much routing.
Yeah, so the issue with this is that if you just look at this, you go, it's beautiful, right? Like I just built a 6 LUT and all I did was draw a few more arrows on it. And I got so much more functionality. I'm going to patent this. I'm going to get a patent bonus. I'm going to be a hero. I'll be the new Friedman. But your issue is like, yeah, this is a ton of routing ports on the inputs and a bunch on the output. And they're both expensive. The inputs in most architectures are particularly expensive, but these are both expensive. So yeah, if you were to actually build this, it's worse. It's too expensive, basically. Like you've greatly increased the cost of the 6 LUT and then improved your ability to reuse things, but it's not a good trade-off point. Okay, so the alternative is to build, so that was called a composable LUT, and the paper talks about that as one option, but another option is a fracturable LUT. So it's the same idea. So here's and you can do this in a few different ways, but this is the cheapest way. So this is my 6 LUT, right? 5 LUT, 5 LUT, and in a 6 LUT, these two 5 LUTs, they both have the same inputs, right? You send the same inputs to both of these, and then you have one or more input that controls the last stage of muxing and get your output. So that's a 6 LUT, and I've just drawn it with the two 5 LUTs that are inside it. But I've added actually no circuitry, okay? So now I want to add in the ability to use these 5 LUTs. The cheapest way that I think you can do that is you literally just bring this output out, okay? So I added one more output. I didn't add any more inputs. I didn't add any more muxing. So what have I got? Well, I've still got my 6 LUTs. But now if I only want 5 LUT, if I don't need that 6th input, I don't have a 6 LUT function, I can basically I could just basically set this input to be ground, for example, and I'll always get this upper 5 LUT coming out of here on the 6 LUT output. Okay, so I've got one 5 LUT function here, and I got a different 5 LUT function on my other output. And I added very little, one output port. So it's very cheap. I mean, there is a trade-off here. Like, what is the trade-off I've made?
If you want to use the 5 LUTs, they have to share all of the same.
Yeah, so the 5 LUTs are much harder to use, okay? Because all the inputs are the same. But they're not impossible to use, right? So you can, I mean, finding two 5 input functions that share all their inputs is possible, but it's a little bit unlikely, but it is possible. But the thing is, I also showed you that there are lots of 4 LUTs and 3 LUTs and so on. So let's say I put a 4 LUT in here and a 3 LUT there. Okay, that only needs to share 2 inputs, so that's not so bad. I even had some 2 LUTs and 3 LUTs. Well, I could put a 2 LUT here and a 3 LUT here and not have to share any inputs. So I've still got, you know, I've got some constraints, but actually there's still some hope that I can find ways to use these 5 LUTs. And my cost was very low. Okay, so this is basically what Xilinx does. Okay, so Altera did fracturable LUTs first. Again, you can often tell, I guess we're not quite sure that fracturable LUTs are the right way to go because Microchip is the holdout. If they choose to do this, then we can say, well, okay, it's sold, but we're not there. But I know, you know, so I was part of the team at Altera that did this. When Xilinx adopted it, 3 years or so later, it is interesting. You had to go, okay, I think we made the right choice because some other design team has independently validated that this is a good idea. So usually then it's going to stay for a while. But this is somewhat different than the way that it was done in the Altera paper that you read. So Xilinx went for the approach of minimize cost. So no extra input routing ports, one extra output routing port, but we still get some use out of this, right? Okay, so what Altera did is they actually spent more area to get more flexibility. So they built a fracture roulette as well, but their fracture roulette looks slightly more complicated to describe. Okay, so here's a 5-let, right? Here's another 5-let. So I got two 5-let outputs. Each has its own mux. And then actually this one I'm just reusing. This is a special mux. And then I've got my 6-let. So I've got two 5-let outputs and a 6-let output. And this is a little complicated looking, but basically they put some extra inputs in. These 4-lets, they share two of their inputs, but then the top two 4-lets get two other inputs, and the bottom two 4-lets get two other different inputs. The net impact is they have 8 inputs. Okay, the paper calls this a 6,2 fracturable let. So you can make a 6-let, it has 2 extra inputs. So when you fracture it, this is exactly how they built that. But the key thing is when I fracture it, I have a total of 8 inputs. Whereas Xilinx, when I fractured it, if you go back here, they had a total of 5 inputs. Okay, so with 8 inputs, it is more expensive, right? I had to actually bring in 2 extra signals from the routing. So that's going to cost me a bit more. And I also got, depending on how I count, one or two extra outputs. So there's more cost to this. But actually, I'm going to skip forward one. They can pack more things. So what can they pack? They could do they've got 8 inputs. They could do a 5-let and a 3-let. They could obviously do a 6-let. They could do 2 4-lets. And they can do things like a 5-let and a 4-let if they share one input, or 2 5-lets if they share 2 inputs. That actually gives you can usually find that, right? There's actually a lot of combinations. Lets do tend to share some inputs, so the odds of finding some of this is very good. Altera did one last thing in Stratix 2 that's kind of tricky. You could actually do 2 6-lets that share 4 inputs. Okay, so the inputs is kind of obvious. You have 8 inputs. You can build 2 6-lets. Well, you have to share 4 inputs so that you don't run out of inputs. But the way this works is they have to have the same truth table, right? The SRAM cells are quite expensive for a 6-let. You have 64 of them. So if you basically made 2 separate truth tables, you basically made pretty much everything for a 7-let. So that sounds kind of insane. So this last way that you use the 6-let, you have to have the same truth table and 4 shared inputs, which sounds like it would never happen, but it actually happens in crossbars. So in MUX networks, you will actually have a lot of functions that are doing the MUX function, and you will have basically a lot of common inputs in crossbars. And it turned out that multiplexing is common enough, like building crossbars in end user designs, that this was relatively cheap, so this went into Stratix 2. It was controversial, and while it was relatively cheap, it was in Stratix 10, they decided that relatively cheap was not cheap enough, and it got deleted, okay? So it's a clever feature. It was maybe a little too clever, so it survived for several generations, but then got taken out. And Xilinx never did that one. Maybe that's why, right? So after a few generations, they're like, Xilinx is not doing it. It must be a mistake. Let's take it out. So this is kind of like just a text version of what I just told you. So another way of looking at this is that when we looked at the synthesis results, 80% of LETs use 5 or fewer inputs. A 6-let actually has enough LET mask bits for 2 5-lets, so how could we reuse them? So the idea is pack 2 5-lets together. And if we basically take these 80% of LETs that are actually not 6-lets, and we can pack 2 of them together, if you do the math of how many of these new fracturable 6-let structures do we need, we only need 60% of them, of what we used to have. But probably we can't pack 2 things together enough unless we add extra inputs, right? It'll be too restrictive. So the process we went through was add the extra pins, add the muxing. We did a bunch of architecture experiments about how many extra pins, et cetera, and 2 worked out to be the best point. So what did it gain? So compared to a regular 4-let, It got a 15% delay reduction, which was pretty close to what we got with if we just did 6 LUTs, because we also looked at that. But it actually got a 3% area reduction at the same time. So that was quite a bit better than that academic study, which showed with non-fracturable 6 LUTs, right? That said 6 LUTs are about 17% bigger, but they are faster. We found the faster, but with fracturable 6 LUTs, we could actually do a little better on area even than 4 LUTs. So that's why they went into Stratix 2. They've been in all Altera FPGAs since then, and a couple generations after that, Xilinx also switched to them. So they're not completely dominant. So some of the lower cost FPGAs, so companies like Lattice and Microchip still use 4 LUTs predominantly. I think Lattice may have moved to 6 LUTs recently. So most high-end FPGAs now use 6 LUTs, but there are some that use 4 LUTs. Let's see. So one of the other things this would be a good example of Alex's question of do the CAD tools affect your architecture conclusions? So to get the most out of these fracturable LUTs, what you want to do is tell your synthesis engine that you can make 6 LUTs, but they are more expensive. And synthesis engines never knew that before, right? Like if you told it you have 6 LUTs, it's like, well, anytime you use less than 6 LUTs, you're just wasting stuff. But now if you use fewer than 6 inputs, there's a pretty good chance that these things will pack together 2 to 1. So we had to tune the synthesis tools, like make some changes to make them understand that, and there's some academic work that went and did similar things. And this shows one of the results. If we optimize for area, basically the synthesis tool is told it's a little less desirable to use 6 LUTs. Use them if there's a big gain in terms of how many LUTs you need. Use them if you think you're on the critical path, like it's going to reduce the depth of the circuit. But otherwise, try not to use them. So that's what you get with the red bars. So you get fewer 6 LUTs, only about 15%, and more 5, 4, and 3 or less. If you say I care more about speed, then basically the synthesis tool is a little more generous in its use of 6 LUTs. If it's close to the maximum depth of the circuit, like it's close to what might be speed limiting paths, it'll basically go 6 LUT if it can. So now it still only uses about 23% 6 LUTs, but you get this trade-off. So, and this makes this optimization more effective. Like telling the synthesis tool, don't just use 6 LUTs wherever you can. Use them where you have to. Use smaller ones when needed. This small bar that is 7 LUTs, if you look through the details of the paper, you'll see that this structure can also be used to do certain 7 input functions, but by no means all of them, like just a few 7 input functions. It's no longer behaving like a lookup table, it's just behaving like a function generator. But it turned out that there were certain uses for some of those. One of those 7 LUT functions was useful for building multiplexers. And multiplexers show up a lot in design logic. So there's a few things called 7 LUTs. They're not really a LUT, right? But like no one in the marketing department is going to try to explain that distinction to customers. They're just going to say 7 LUT. Yeah.
I guess for the 7 LUT case and then the 2 6 LUT case with the previous slide, you mentioned that they're kind of used for both crossbar and
Yeah.
but then I'm assuming the FPGA has enough multiplexers and enough crossbars that you don't really have to rely on LUTs to do that whole.
Well, you can't get at those crossbars and multiplexers as like an end user though. Like the routing is built out of crossbars and multiplexers, but the thing is you can't control it. There's no select signal, right? So it does make all your wiring work, but basically it turns out that like we actually analyzed this on a bunch of end user designs, and I remember one analysis showed that like 15% of the design logic was like muxing, right? So there's a lot of muxing in data paths. It might be even higher now. But that muxing has dynamic select signals, right? It's like a packet came in and based on like its ID, you steer it to this unit or that unit, for example. And you can't do that with the routing muxes because they're statically configured. You can't suddenly say, now start changing this wiring to that wiring. Only like the LUTs can do that. Does that make sense?
So I guess it's not like multiplexing 2 different inputs to a specific package. I guess it's
Well,
steering one.
it is steering it. Like let's say you have one multiplier, but you have 2 different things you might want to feed to that multiplier. So you build a multiplexer in front of the multiplier. And the way you build that multiplexer in front of the multiplier is using like the logic block, which is LUTs. Okay, so you're actually programming the LUTs. You send both data inputs into that logic block. You send the select input into that logic block, and you program the LUTs in there to basically do a muxing function. Does that make sense?
Yeah, that makes sense.
There are actually a bunch of papers where this seems to, it drives people a little crazy. They're like I'm surrounded by muxes and crossbars, right? Yet I cannot use them for all these muxes and crossbars in my designs. I have to use my LUTs. I don't want to use my LUTs. So there actually are academic papers where they say, could we just use the muxes and crossbars in the routing to do this function? And they show you can, but you essentially have to like add paths from other routing, right, to bypass the SRAM cells and start controlling the routing some of the routing muxes dynamically. It's kind of, what happens is it makes your routability bad. Like basically you have to route these two signals on these two wires, okay? And then usually these muxes are actually wide data paths. So now repeat that for 128 bits. And now the select signal, you basically route that to these SRAM, to bypass these SRAM cells. And you program these routing muxes in some special mode where they're not paying attention to their SRAM cell, they're paying attention to this other signal. And now we'll do the switching function. But your problem is that actually the routing failure rates get really high because you've made the routing problem much harder. Instead of saying get to this logic block, you're saying get these signals to these specific wires. Right. When we talk about routing architecture, I'll show you that's actually a much harder problem because we've essentially cut away some stages of flexibility. So yeah, academics have looked at this in various ways. How could we reuse these crossbars inside the logic cluster? How could we use the routing muxes? And some of the studies claim, gains, but I haven't seen any of them be commercialized because they also have a lot of costs, right? It's much harder to route.
Especially we have the crossbar block and the CLDs.
Yeah, like you could reuse that. But then once you reuse that, like that crossbar was basically allowing you to come in on sort of different pins, which made it much easier to route. Once you use that crossbar to do switching, you got to come in on specific pins. Right. So now it's much harder to route. So then you have to wind up adding usually a lot of flexibility to the rest of your routing. And then you have to evaluate, is that now more expensive than just saying I'll build more LUTs? So, did you have a question, Jim?
No.
Okay. Yeah, the same thought. Okay. So yeah, good question. If you can find a way to make that work, people will love you actually. So customers will love you, your competitors won't. So.
It seems like it's a question of architecture rather than okay, could we make the routing flexible enough that we don't have to use these weird block configurations for this specific let's do something way more useful.
Yeah, no, and there are architectures that build actual muxes that can be, like instead of in their logic block, they'll have a mix of say LUTs and muxes, right? Because they'll say, well, there's a lot of mux functions, so I don't want to use just LUTs to just do muxing, I'll just build muxes. And there are architectures that have been built with that. And they're not unreasonable, but Xilinx did some of that, and they've now moved away from it and just said use the LUTs. And the basic reason is adding all the pins to connect to the muxes is still expensive. So once you add all those routing ports to hook up to the muxes, you start going, wait a sec, okay, so now I've hooked this mux up to everything, and all I can do is a mux, but I still need all these routing ports. So maybe what I should do instead is not make a mux, but I should make a LUT. Do you know what I mean? That's effectively the trade-off.
Then it seems like you're not able to use the LUTs if you have some that specific logic, like that specific logic block. If you use these extra boxes and routing ports, now you use up the routing ports where maybe you can try to pack another logic with that LUT with the routing knowledge after you put something else.
Yeah. There may very well be a better architecture there, but you have to basically think about the routing and the logic simultaneously, right? So, okay, so same paper, so they like fractional 6 LUTs, this is their design. They now need to decide, okay, how big is the logic block? And the paper gives a bunch of results on basically how many of these, they call them ALMs, which in the paper they inexplicably call ALEs, because that was the engineering term. So they can make 6 of these fractional LUTs, 8, 10, 12, etc. And they check, well, what does that do to essentially how hard it is to route? Like how many inputs do we need to the logic block? So that goes up, as we already saw. If you add more and more stuff to the logic block, you need to add more inputs, which Altera calls lab lines. That's like the inputs to the cluster. You need to make your routing channels wider. That's because the number of used inputs per logic block is going up, so that lambda is getting higher. And then speed, it's not clear what's going to happen. And then area, there's a complicated trade-off because you need a wider channel, but you need fewer logic blocks and stuff. So what they found is 10 is, for Stratix 2, they did 8. And for Stratix 3, they changed that to 10. And that's where they've been since. So they found a relatively large logic block is kind of the reasonable place to be here. So there's a trend for logic blocks slowly getting bigger. So this, like basically Altera and Stratix went from, I think it was like 10, I think it was 8 4-LUTs to in Stratix 2, 8 fracturable 6-LUT to Stratix 3, 10 of those. And we'll see Xilinx is also making their logic blocks bigger. So there's a trend for logic blocks to slowly get bigger. Okay, so we saw that academic paper, the Ahmed and Rose paper, where it said we can make the number of inputs equal to the LUT size divided by 2 times the number of LUTs in the cluster plus 1. And that'll let us have high logic utilization. So let's see if that agrees with Stratix 3. So they basically said they needed 46 inputs for 10 of these 6 LUTs. So 6 divided by 2 is 3, times 11 is 33. Okay, so this formula from Ahmed and Rose says we should only really need 33 inputs, and that should give you really high logic utilization. So why did Altera actually build 46? And in fact, in the real chip, they added a little more margin still and built 52. Okay, so why, yeah, Ahmed and Rose would say you only need 33. Why did Altera just not read the paper?
I guess.
What do you think?
For Ahmed and Rose, for that contribute to the two lines or two, the average of the 90%.
Yeah.
90% isn't 100%.
Yeah, so I guess maybe Altera really wanted 100, but that's an expensive way to get to 100. Do you know what I mean? Because this is not a cheap thing to go from 33 inputs to, well, 46, but really they built 52. All your crossbars get bigger, all your connectivity, the number of routing ports of the routing goes up. So it's pretty expensive, and the whole thing you're chasing is that last 2%. Probably not a good idea. So what do you think?
Maybe because this is average, but we need to think about both.
Well, the Ahmed formula said that that was enough for kind of the worst case. But like you could get 98% of your clusters completely filled. Did you have a thought back there, or just, yeah? Yeah, and in fact, I can do even more. I could use k equals 5. And I got a pretty good chance that I could use all of these in 5-LUT mode if I got some shared inputs. And very good chance I could use them in 4-LUT modes. So yeah, that's exactly, you have to actually think of that. That formula actually works, but don't just think of them as 6 LUTs, because they won't always be used as 6 LUTs. If they're used as 5 LUTs, and you put it in that exact formula, you actually get 52.5, much higher. And yeah, what they really built is 52. So in the table it says they would use 46, but then in the either the text or I know in the chip what they did, so they really did 52. So, and that might be for layout reasons or all sorts of stuff. They might actually add some guard band, or maybe when you do the layout it turns out 52 works a bit better and the cost space is very flat. Yeah.
Okay, so the ALE is like many of the basic.
Yeah, and one thing I'll just do here is ALE means ALM.
Yeah.
So, yeah.
And then the lab is many ALMs.
Yes. So lab means logic block in Altera terminology. In engineering, when we were developing this, we called this the ALE, like the adaptive logic element, and then marketing didn't like that term. They were like, this is the adaptive logic module, which is why it has like a name in this paper and then a different name in all Altera literature.
Okay, so lab is the cluster and then ALM is the basic cluster.
Yeah.
Okay.
Let's see. And I think, let's see what slide I'm on. Okay, let's take a break there, actually. How about we take a break till like 7 o'clock? And then we'll talk about some other stuff. I'll move this out of the way. Okay, so another question you have in making these logic structures is how many flip-flops did you put in? So in the adaptive logic module, that fractionable 6 LUT in StratX 2, one of the questions was, well, how many registers? Should we have a register for every 6 LUT, which what I've shown here, or should we have a register for every 5 LUT? Which basically would be I'd put more registers in. So what do you think? Should we put one per 6 LUT, one per 5 LUT? What do you think, Adam?
I guess it depends on how bad is the routing delay. Because if the routing delay was like not that bad, then it doesn't make sense to put a register on the output every 5 LUT, just because it adds some area cost because you're adding registers. You're increasing your latency too, which is not the worst thing in the world, but I guess it's most important. But I guess I would be more concerned with how bad the routing is. So it's not bad. Keep it as it is. I guess keep it as it is. If it's really bad, then maybe have it.
Okay, so you worked at Microchip, right?
Yeah.
What do you think? Is routing delay bad? It's beloved by end users, or is it good?
No, it's worse now.
Nobody likes routing delay. It doesn't. So of your two choices, which one do you think you're going to go for?
I'll probably go with one per 5 LUT. 6 LUT.
Yeah. So and that's exactly what was done. Yeah.
So here we have 1.5. So you have 10 ALMs. You put 5 of them with 2 flip-flops and 5 of them with 1.
I sentenced you to write CAD tools for complicated architectures for 5 years.
You already do.
Maybe I did. Yeah, one register for 6 LUT leads to register starvation for many designs. Registers aren't that expensive, so in FPGAs it's usually a good idea to be generous with registers. Routing's relatively slow, and registers are relatively cheap compared to LUTs. So we added another register. It's pretty cheap if you don't add routing ports. So the register itself doesn't cost too much. So what Altera did, as described in that paper, is 2 registers per ALM, so 1 for each 5 LUT, but keep the number of routing ports the same at 8. Okay, I already have 8, so we can make this fractionable 5 LUT more usable. Let's stick with that. Adds in a couple of very small 2-to-1 muxes. So that's a much smaller mux than like what you would build to connect into the regular routing, so it's not too expensive. The idea of these extra little muxes is to let registers be used sometimes when they're not directly fed by the LUT. So the best way to use a register, like what FPGA CAD tools really like to do, is LUT feeds a register. Okay, so this is like preferred way to use a register because this path is really fast, so it's kind of a speed win. It's also essentially an area win, right? Like you saved something from coming in from the general routing. So that's his preferred way to do it. But you will get cases where, well, this LUT doesn't have a register right after it. So this register is just going to be wasted. That would be fine if there was no demand for registers, but designs are getting more and more register rich, right? People are pipelining deeper, so you get shift registers. You do just to align all your data. So sometimes you do wind up with significant numbers of registers that are just one register feeding another register. So there's no LUT that you could pack it with that's feeding it. So you have to hook that up to a routing port. And in this case, what the StratX 2 architects did is there's an extra connection. So this basically is done with a 2-to-1 mux here. So it's not shown here, but basically you have to have 2-to-1 muxes to allow these two choices. So I'll just draw them in now. Basically, this could come from this path, or it could come from like this input, okay? So adding this extra 2-to-1 mux lets me connect the register output back to one of the LUT inputs. Why is that useful? Well, maybe this LUT doesn't feed any register, it just feeds another LUT or a multiplier or something, but maybe I can find a register that feeds it. And if I pack it in here and use the special 2-to-1 mux, I basically don't need a routing port, so I can use the routing port I just freed up to basically feed into the LUT. Okay, so it makes it, or feed it to the register. So it makes it easier to use this register. So it is an area win. It's actually a pretty significant area win. We found that we could basically reduce the number of ALMs we needed by 9% by putting this in, because we could basically use these registers better. This one's even more basic. We've never even experimented with taking this out. This is the most basic way to use a register. This is a speed win too, right? The fact that instead of going through some kind of regular local interconnect, the fact that we can directly feed from a LUT to a register speeds everything up. What do you think about this special connection? Is this going to be a speed win? So it definitely helps with area, right? Saved us a routing port in a bunch of cases, let us use our registers better, and didn't cost much. Just cost us this little 2 to 1 bucks. So what do you think? Is it also going to speed things up? You might know the answer to this, so I'm not going to ask you yet. So anybody want to guess? You got a 50-50 chance. If you've been sitting here going, I want to ask her a question, I want to answer a question, but I'm too scared, it's like it's 50-50. If you have no idea, it doesn't get any better than this, right? So what do you think?
I think so, because for us, let's say that path wasn't there, you would have to go off the like local interconnect to go back onto some other. Like,
Yeah, my next
bus
choice,
or something.
yeah, so let's draw that. Okay, so if I didn't have this little mux, which is quite fast, I'd have to go back out to basically the cluster local interconnect, which is some big crossbar, so a bunch of muxes, and I would come back into here to this routing port and go in here, right? Or maybe I wouldn't use this routing port, but I would come in through this path, and it would be slower. So seems like it should be a speed win for exactly the same logic. This is a speed win, right? Was not a speed win. And I was actually on the team that did this, so we all thought it would be a speed win too, was it? So that's why I asked you guys. So okay, I feel better that nobody here thought, everybody here thought, well, the one person who answered thought it was a speed win too. Adam, why do you think it's not a speed win? Or do you think it's a speed win too?
No, I'm struggling because there's a feedback path, and then to me, like, it's with feedback paths, it's hard to cut them more.
So this is really fast. Okay, so this connection was like, I can't remember the exact number. Say this is like 50 picoseconds, or actually it was really fast. Say it was 30 picoseconds, and going back through the local interconnect, this crossbar, was more like, this generation probably like 300 picoseconds. So the connection itself electrically was a bunch faster. 30 is probably too little. Let's go back to 50.
My assumption is that there's probably going to be more registers cutting on external paths. Because I'm thinking like, because another thing that I'm sort of thinking related to this is you also just register inputs, let's say.
Yeah, so I think you're on the right track. So that's actually, once we saw this, we figured out why it happened. It was kind of interesting that all of us had the wrong intuition. So this connection is much faster. So you think, well, it should speed things up just like this one did. This connection is the end of a timing path, right? Like all timing paths start at a register and end at a register. So for sure, any critical path that was going to end at this register, we just sped up, right? Because all paths ending at this register go through this connection. For this LUT, where we sped up a timing path, the start of a timing path, right? Like we made the path from this register to this LUT faster, but this LUT has other inputs. So there's something else driving this input. Maybe it's a LUT, or maybe it's a register. If it's a register anywhere else, it's slower. Okay, it's got a higher delay. If this one has a LUT, and that is fed by a register, well, that's even worse. There's like a register, some routing, then a LUT, then some more routing, and then you get here. So we basically sped up a path that will never be the critical path. It's basically guaranteed to always be, after we make this enhancement, it's guaranteed there's some other path on one of the other LUT inputs that will be slower, so it doesn't speed things up. So it was interesting. None of us realized that, right? We were all quite disappointed when it didn't speed up, but it was still a good area win. So
Why did it help area?
it helped area because of the fact that we could use this register better, right? If we didn't put this little 2 to 1 mux in here, then, well, this routing port is already taken, and in the case I've shown you, we just couldn't use this register, right? So you had to subtract the cost of the 2 to 1 mux, but that was quite small. Okay, and designs just keep getting more register rich. So in Stratix 5, so 3 generations after the paper you're reading, it's the 6 LUT structure is still pretty much the same, but it went to 4 registers per ALM instead of 2. And the reason for that is, basically deeper and deeper pipelining, so that you're getting like, to line up, remember when you pipeline, you have to increase the latency of all the paths you cut, right? You have to find these cuts that disconnect your inputs from the outputs. So you wind up with some shift registers usually, where you just have registers feeding other registers because you had to cut those paths. You might even have multiple registers in series because you need to get across the chip and that actually takes multiple clock cycles, even with no logic. So this went to 4 registers per ALM, but still has 8 routing ports, and it actually is making it harder to use these. So basically, the registers, to use all 4 registers and use the LUTs becomes kind of difficult, right? Because they are all fighting over these routing ports, but sometimes maybe you won't use the LUTs in those cases. Okay, so if we go to Altera's most recent FPGA, which is Agilex, which is at 10 nanometers, and I can't quite figure out now if there's a 7 nanometer version or not. Maybe one of the Altera people could tell me. No one can tell the process numbers now appear to just be like every 6 months decrement the number, so I can no longer tell. Okay, so some changes in this one. So the first thing is their local interconnect is more complex. So let's see if I can explain this on this figure. They have some local interconnect that basically the signals span the whole logic block, which looks a lot like their older, like the local interconnect of their other designs, where it's kind of like a crossbar or a partial crossbar. But in Agilex, we'll read the paper on this later, but basically wire delay is getting bigger. So even inside of a logic cluster, they're saying that these wires that span the whole height of the logic block are starting to get a bit slower than they'd like. So they've made some wires that are only 1/4 the height of the logic block. So what that means is essentially their local interconnect is a bit more complicated. They have like kind of 2 wire lengths. They have one that's 1/4 of the logic block and another wire length that's the whole logic block. So it's kind of like they've added another level of partial hierarchy inside the logic block because long wire delays, and these are not really long wires, but even those wires are starting to get a reasonable amount of delay. And we'll talk more about Agilex later when we read the paper on it. They made a whole bunch of changes in the routing architecture, but this is one where they changed the local interconnect in the logic block. Okay, so any questions about that? Okay, so we talk a little bit about Xilinx and how they're the same or different than Stratix 2. So I already showed you one of Xilinx's fracturable LUTs. So their original fracturable LUT that they used for many generations was basically as cheap as they could make it. And it's shown here. So 2 5 LUTs, they share all their inputs. And if you use it in 2 5 LUT modes, you have to ground the 6th input. And now basically one output comes out on the 6 LUT output and one comes out on the 5 LUT output. So no extra inputs at all, just one extra output, but you got to have 5 shared inputs to use 2 5 LUTs. Or you could do a 3 LUT and a 2 LUT, et cetera. So they're less flexible on how many inputs they can handle, but they are more generous or easier to use their registers. So they build 2 registers, one on the 6 LUT and one on the 5 LUT, or you can think of it as each of the 2 different 5 LUTs. But they basically build a special routing port that goes into those 2 registers. So they can either be fed by the LUTs, the 6 LUT and the 5 LUT, or they can bring one of their signal in to feed one of them directly, which is kind of a little less complicated than the patterns that Altera has. So it's kind of interesting. Their LUT packing is a little harder. Their ability to stick registers in is a bit easier. And one thing that this may help them with is, kind of this is where CAD may affect things too. At least all the time, I think this is basically still true. Quartus has a packing step relatively early in the flow, right? Where it basically decides what's in a logic block. And that can handle a lot of legality constraints. So if we have all sorts of rules on which LUTs and which registers can go together, that packing step can handle it. And then we can finish off the placement and do the routing. Xilinx doesn't do as much packing. They more try to place the low-level primitives. And a benefit of that is that they can move, if they're doing that, they can move these registers around more easily late in placement if they don't have as many constraints. And I met a couple designers who they liked, this is my latter years at Altera, they liked Quartus's optimization overall, But one of the things they liked about the Xilinx style of CAD was they found if they added pipeline registers kind of late in the design, it was easier for them to go in and stick them in certain spots because they would probably legal there. And in Altera's architectures, there was a higher chance they were illegal because the whole CAD flow was kind of built around we get to pick where the registers go, not the designer tries to put them in at the end. So for kind of those incremental changes, the Xilinx architecture was essentially easier to understand. You put the register in and it's probably going to be fine. Yeah, so let's see. So Xilinx has made this 6-LUT structure slightly more flexible in Versal. In Versal, basically, you can use 6 inputs when you have the 2 5-LUT modes. So it's a little more flexible now. Not as flexible as what Altera does, but closer. Okay, and then the other thing that Versal did, and we'll read some Versal papers later too, but on the logic block side, they've gone to a bigger logic block. Okay, so until Versal, their logic block was basically 8 of these fracturable 6-LUTs, so it was a little bit smaller than Altera's logic block. And in Versal, they said, we're not getting enough signals captured by our local routing, so we're going to make the logic block bigger. It's going to have 32 of these fracturable LUTs. And they also, basically, this is a chart from that paper we'll read later. They're saying here that in UltraScale, so their last generation before Versal, they could only basically route a relatively small fraction of things completely inside the logic block. Most things had to go out to the routing and come back in. And in Versal, by making the logic block bigger and making their local interconnect essentially more flexible, now 15% of their connections they could kind of keep just inside the logic block. And they considered this a win because the local routing can be smaller and faster. So what's interesting here is Xilinx for many years essentially has had somewhat less flexible local routing than Altera and a little bit smaller logic block. And in Versal, they decided, nope, we're going to make really big logic blocks and we're going to make our local routing more flexible. Altera basically said, we're going to make our local routing a little bit more complicated, more like the way Xilinx has had more complicated logic, local interconnect. So it's a bit interesting. There's some convergence, but there's also some that are going in slightly different directions. And again, the Versal logic block also made their 6-LUT a bit more flexible. So this is a picture of it, and it might be a little too complicated. But basically, if you count it carefully, they now have a total of 6 inputs that are usable when you're in 5-LUT mode. Basically, you got 4 shared inputs here. The 5th input goes to this 5-LUT. The 6th input goes to the other 5-LUT, right? And if you're in 6-LUT mode, then the 5th input goes there and the 6th input goes there. So they didn't build like extra inputs to the logic block, but they took the 6th input and basically added a little bit of extra muxing so that when you're in 5-LUT mode, you can still use the 6th input. You just use it for the other 5-LUT, giving them a bit more flexible packing. Okay, and that is it for for basic logic blocks. I was going to talk about one other thing, and I think my slides didn't update, so let's see. Okay, so let me switch to the chalkboard for a few minutes. So any questions on any of that? Yeah.
I was curious who patented the fractional LUT, and then because I noticed Xilinx just kind of took it, and I'm wondering did Altera's patent?
Oh no, we patented it. I think I'm one of the people who patented it. So.
So did they just kind of dance around no, this is not fractional. This is a broken apart LUT.
Okay, do you want, Okay, so at the time I joined Altera, Xilinx and Altera was spending $5 million US a quarter on litigation. It was believed that because Xilinx was a bit bigger, they were spending more than that. So we were suing each other. Like, I wasn't personally suing anybody, right? But the two companies were suing each other over various patents. We were also, I think, Lattice was suing us, we were suing Lattice. Everybody was suing everybody, basically, and it was just going on forever. And it was literally like there would be incentives in the company to patent key things to protect them from your competitors, but also because everybody knows they're all litigating each other, so you have to have patents. You violate their patents, you assert your patents against them. When the technology crash happened in about 2001, 2002, one of the things that happened in the, I guess, many industries, but includes the FPGA industry, is suddenly this litigation seemed too expensive. So basically, all the companies settled the lawsuits and cross-licensed each other's patent portfolio.
Oh.
Okay, and agreed. So Xilinx and Altera agreed not to sue each other again for 5 years. Like we're both licensing each other's patent portfolios, and we will not do any further lawsuits on new patents for 5 years. So there's two ways so basically there's two things that you could do. There's a patent, you can design around it, right? So you can go, well, this patent covers this, but it doesn't cover that, so I'll do something different. Notice their fractional LUT's not exactly the same as the Altera one. Now, we would have tried to make the patent as broad as possible, but if somebody, say some academic, had proposed something like this, but not exactly what Altera did, you can't make the patent broad enough that it would have covered that.
Right.
Okay, so how broad you can make it is limited by what's been published. So that's one possibility, is that they basically, and I'd have to go back and look at the patent very carefully to see that. Are they different enough that they wouldn't infringe? And that's possible. The other one could be that they might infringe, but we got lots of patents, they got lots of patents, and we're not suing each other at this point because it's probably just going to result in a bunch of legal fees again. And there is some of that too, that if you aggressively apply your patent portfolio against everybody, this is one of the reasons companies want to have patents, like larger companies, is they assume someone will sue them, and one of the things they need to have is patents to sue them back with. That works well with large companies. Where it doesn't work well with is patent trusts. Patent trusts are these often called patent trolls, where they bought up patents and they have no products. You can't sue them for infringing your patents because they don't do anything. So that's a challenge. Those ones are kind of just a tax on the whole industry. So anyway, I don't know if that answers your question or not.
No,
So,
I was really curious because
yeah. Any other questions? Okay. Let's see. Yeah, so actually, I got to say one other thing. Some of these lawyers were kind of amazing, right? Like, so this was Cypress Semiconductor sued, hopefully TJ Rogers is not watching this, probably isn't. Cypress Semiconductor was one of Right-Track CAD's customers. Altera was their other major customers. And after we were bought by Altera, like a year later when Stratix was coming out, Cypress sued Altera saying, we want that architecture. We were working with Right-Track too, and we should have royalties on that architecture. Which Altera is like, you are not getting royalties on that architecture, it's our architecture. So now they're having a battle over who owns what. And it was pretty clear Cypress did not have rights to this, right? But you have a lawsuit anyway to sort it all out, because if they could get rights to it, it'd be extremely valuable. So I was like a key witness in that. So I was basically brought down by the Altera legal team, which was like large, right? Like this is where it's incredibly expensive. You have teams of lawyers that are talking to you. And the head lawyer for Altera, I remember I was being deposed. It means like for a day, Cypress's lawyers are asking me questions and going through my old notebooks and everything, trying to figure out, did I ever do anything bad with intellectual property that belonged to, that we were doing for Cypress and we shouldn't tell Altera. And I remember like there was one question about a certain part of a particular Altera architecture, a detail of like the logic and the routing. I said, yeah, I think it's, I think that was in the 10K, that was this. And our chief lawyer said, yeah, no, it was in the 10KE, right? And I was like, how do you know that? And so he was amazing. He said like the stack of documentation for all this was like 10 feet high, and about 80% of it he had in his head. And he really did. Like this is something where I wrote the CAD tool for it. So I had to know this detail about the architecture. So I did know it at one time, but he now knew it better than I did. Anyway, so I'm sure he charged a lot of money for that. So that skill was probably quite valuable to him. So, yeah.
Just curious, does the lawyers have a technical background?
Most of them did. Yeah, most would have, like, so patent lawyers almost always have an engineering degree if they're going to work in the semiconductor field. For those litigation lawyers, most of them also had an engineering background. I can't remember if that person did or not, but he certainly knew lots by then. So,
He did political science and just really dabbled in FPGA tech.
yeah, I mean, litigation is its own thing, right, where it needs its own skill set. So, okay, so let's talk about arithmetic. Okay, so we talked a bunch about LUTs, but there's another thing that's important in logic blocks. So arithmetic. So we can build anything out of LUTs. So we don't need to do anything special for arithmetic. We can just build it out of LUTs. But let's see how well that works. So let's say we want to do sum becomes a plus b. Okay, and these are not 1 bit wide. For arithmetic, usually we're working with wider words. So we'll say those are all 32 bits wide. Okay, so let's build that out of LUTs. So structure looks like this. So I'm just going to build a ripple carry adder out of LUTs. Okay, so I got A of 0, I've got B of 0. Those are going to the LUT, and I can compute sum of 0. Okay, and okay, go to another LUT, and they're going to compute C out of 0. Okay, which is going to go down here. Try that pretty messily. Let me erase that. Okay, so I'm not going to draw this whole thing. That's like the first 2 bits. Okay, so I take A of 0, B of 0. From those I compute sum of 0. A of 0, B of 0. From that I compute C out of 0. C out of 0 goes down to my next bit in the adder. So I take A of 1, B of 1, and C out of that previous thing, which, let's see, what did I do with it here? That's my C out. Yeah, okay. So my C out is going here. That produces my sum out. I take those same 3 signals, A of 1, B of 1, and C out of 0, and I produce my C out of 1, and I just repeat this, right? So ripple carry adder. So how many lookup tables do I need for this 32-bit adder? Right, so I need 64 LUTs. Okay, so the depth of a circuit is like the number of things in series on the critical path. So for this adder, how many LUTs do I have in series? Yeah, so I have 32 LUTs in series, right? All the way through the whole carry chain. So those 32 LUTs will be my critical path. Okay, so how long does that take? Let's say the delay of a LUT plus the routing to get to the next LUT is maybe 500 picoseconds. If you're looking at like a really recent chip, you might do a bit better than that, but it's the right ballpark. Okay, so if I take 500 picoseconds times 32 stages, that is 16 nanoseconds for a 32-bit adder. Which is 62.5 megahertz. Okay, just to do a 32-bit add, right? That's not doing anything else in the same clock cycle. So it doesn't sound so good, right? Like, what if I need to do a 64-bit add? What if I need to do something before or after that? This is pretty speed limiting. So that looks pretty bad. Okay, so let's just compare that. Let's see if just LUTs are just bad at everything. Okay, so let's compare that to some other functions. Let's compare it to a 32-bit AND. Okay, so out is A and B. Okay, so what does logic look like for that? So I have an A of 0 and a B of 0. And a LUT's going to produce out of 0. And then I go all the way down to the last one. Of A of 31 and B of 31 produce out of 31. Okay, so it's pretty easy. How many LUTs? Okay, so 32 LUTs, so a bit better. Half as many LUTs, so that is better. They're 2 inputs each. Okay, so not fully used. It's a pretty good chance that I'm going to find some more logic to pack in with them. So if I've got and ORs and so on, this will all pack together pretty well. You could say, well, maybe you can find some stuff to pack into this too, but it's a lot harder, right? Like this structure is kind of more convoluted, this linear chain, and I am using 3 inputs for each of these LUTs. So I'm already using more of their inputs. I may be able to find some stuff that came from A and B here. So maybe I can pack some stuff in here, but I got more unused LUTs here. So the area is actually less than half. Let's see. Okay, so basically, but easy to pack more. You know, so for example, if this was in something like A and B or C and D, now I can pack all this stuff together in one LUT. It'll use all 4 inputs. So I could do all this instead of the A and B, and it won't cost me any more stuff. And there's a pretty reasonable chance I'll find something like that. Okay, so that's our area. What's my critical path? Yeah, so so the critical path is the really big difference. The critical path is 1 LUT. Okay, so with my same estimate of how fast a LUT is plus the interconnect, I get basically 500 picoseconds or 2 gigahertz. Okay, so this is a pretty simple operation, but it's not speed limiting, right? Like I've got no problems with speed here, but I already had a problem with my adder and speed. Okay, so let's see, let's get rid of this. Okay, so this sounds pretty inefficient, but maybe it's not a big problem. Maybe we don't do arithmetic very often. So what fraction of logic in an FPGA do you think is doing arithmetic? So add, subtract, things like that. What do you think? Do you have a guess or a different question?
I guess the first reading, block below last 1%.
It's an excellent guess. Yeah, so arithmetic is common. So it's typically like 10% to 30% of a design. And it's maybe rising, right? Like as people do ever more signal processing and deep learning, that number may be moving up further. So it's a lot. If this wasn't very common, then we just wouldn't care about it. There's lots of stuff we do that's not efficient, but doesn't matter if it's not done much. But this is very common. Okay, so it's inefficient in LUTs. Right, so it's 2 bits or 2 LUTs per bit, so it's area inefficient. And even worse, it's got a long critical path. Okay, so what do you think? Is this a good choice for a hard block? Usually if we decide to harden something in FPGA, I want it to be common and inefficient. Those are the two things that we want. So what do you think?
Excellent choice.
Okay, so yeah, so I think it's a good option for a hard block.
Harden half of it.
Okay. I mean, is there anything else I could do about this critical path before we go and harden it? Like, can we just fix this somehow, some other way? Yeah, what do you think?
Could you just add a bunch of registers and have the retimer deal with it?
Well, you could put registers between all the LUTs. So in this case, I'm doing it all with regular LUTs, so I could put registers everywhere. That would solve my critical path problem, although it means I've got a large latency. So like, it means like I do a 32-bit add, I need 32 cycles of latency, which may be an issue in some design, in a lot of designs actually. Like you maybe go, I need registers everywhere to latency balance that, right? And sometimes FPGAs, one of their strengths can be low latency processing. So I said registers are cheap, pipeline is a good option. It is, but sometimes you're not trying to pipeline to that extreme level because you might be going for low latency operation. Yeah.
I guess the first, just on a, based on a historical perspective, since the critical path is the carry chain, just part of that, and we just have to have also.
Yeah, so you could make, we could make a new hard block, or you're saying maybe I just harden the carry chain itself. Yeah, we're gonna look at both those ideas, so that's a good idea. The other thing you could do, let's say the FPGA companies are just like, we're not speeding it up. What would you do? Yeah.
You could like use a different identification of carry select.
Yeah, so there are faster adders than ripple carry adders. So you could build a carry select or carry look ahead adder out of these LUTs. It will be faster, it will take even more area. So if there was no better solution, then that's what people would do. But it's still not a great solution because they'll burn more area to try to claw back some speed. Okay, so I'm going to start with, let's see. I'm going to start with a hard block. So Adam has a good idea, but we're not going to do that right now. We're going to first try a hard block because that's the first thing to think of when we've got something that's inefficient in common. Okay, so let's make it this special hard block. So I'm going to build my new adder block. Okay, so I got a full adder, full adder, a full adder. I'm going to write, these carries are my problem. So the carries are now just wires going between these full adders. I'll probably make it more than 3 bits. Yeah, let's make it a bit more than that. Probably I'd make this a whole bunch of bits, maybe 16 bits or something like that. I've got a bunch of inputs here. I bring in A and B. Now they both have many bits. I bring out my sum. It also has many bits. So yeah, let's say each of these numbers is like a 16-bit quantity. Okay, so I'm doing 16 bits of summation in this. What do you think? Does it look good? Adders are not very big. Okay, so to build a full adder is a few gates. This is just a wire. I don't need any programmability. So I just built a 16-bit adder. It's not large. And what I could do now is basically, maybe I'll have a logic block and then I'll have one of these. And I'll have another logic block and I'll have another one of these. So that's my proposal. What do you think?
What is the subtraction? Oh no, wait, no, that was a stupid question. We can just choose complements. But let's say we have to do that.
Aha, I just solved your problem. Okay, so I got LUTs. My LUTs are going to complement this, and I'm going to make C and win. I'll give you a subtractor. Problem solved. We now have an adder, but it is a good idea. We want to make hard blocks as flexible as we can. This is no longer my adder. This is my adder/subtractor. So that actually would be a better design. So let's do that. So I should put the C in. Otherwise, I can't do that. So what's that? I should do a C out too, sure. If I don't do a C out, I can't combine these into like larger bit widths. So I need a C in, I need a C out. What do you think? Do you like it? Alex, what do you think?
So if you're going to make it its own tile, you're saying these adders are really tiny, and they're so tiny in fact that you want to try and like match the size of the CLBs, which ends up being like you're going to need to put a bunch of adders in there, which is going to need to require a ton of inputs.
Okay, so you think basically this is going to be a pain to lay out because I put in a tile of this and a tile of CLBs. This is too small. And I guess tiles do get routing channels and stuff. So yeah, like you're right, it is going to be a pain. There's also, is this cheap? These adders are really cheap. What about these? How many inputs do I have? I got 32 inputs. I got 16 full adders. That is approximately 0. right? And I got 16 outputs. Well, and another couple, right? So I've got maybe 17 outputs and 33 inputs. How expensive is it for me to build all those routing ports? That's on the order of how many inputs and outputs I have for a logic block. So from a routing perspective, this thing is close to the cost of a logic block. From the perspective of what I put inside it, it's a tiny fraction. But so when I actually put it in, it's going to be hard to lay out, you're right. It's not pitch matched to the logic block. That's going to be a pain. But it's also way bigger than I thought because of the fact that I got to get all these signals to it. So it's got many inputs and outputs. So it's got a lot of expensive routing ports. So it will still solve my speed problem, but it's going to cost me a lot more to do it than I ideally would have done, right? There's another thing. If I'm going to make basically a logic block, and then I'm going to make my adder subtractor, and then I'm going to make a logic block, and then I'm going to make my adder subtractor, or maybe I'll make 2 logic blocks, 2 adder subtractors, etc. I'm going to get parts of my design where I only want logic, and other parts where I might have a cascade of adders, like an adder tree or something. So by having 2 different kinds of things, I will tend to stretch my wiring some. Like I am making the placement engine's job harder. And you could kind of go, well, maybe the adders should be somewhat together. Maybe the logic blocks could be somewhat together. There's no perfect answer, right? Like every design will want it a bit different. Some designs will want more adders, some will want fewer, etc. So we're going to stretch some of the wires. Okay, so we'll stretch some wiring in placement. Like a placement engine would love to just have a homogeneous chip that's all one thing, but it's too inefficient, so we can't do that. But every time we make these different things, we do make the placement engine's job harder. We do stretch our wiring a bit. Okay, so stretch some wiring in placement, and we're going to have that's going to lead to some increased delays to and from the block, because it will tend to not be quite as close as the next logic block would have been. Now, if I had no better ideas, I should still actually do this, because it does solve my critical path problem. Or I would probably still wind up doing this. But maybe we can come up with a better idea. Okay, so is there anything else we could do? I think Adam already kind of came up with the answer. So you said harden the carry chain. So you're saying don't make me a special block. I think essentially what you're saying is put some special structures inside the logic block.
Yeah, because the carry chain is what's actually like contributing to the critical path. Because if you were just doing the sum not like half adders, that's fine.
Yeah.
Actually, it's the carry chain that cascades through everything.
Yeah. Okay, so so I'm going to write that idea down as basically add it to the logic cluster. Okay, so why is this good? Because the logic cluster already has all these routing ports. We'll reuse them. Okay, so one way we could do that is we could basically say we've got a logic block and you can either use the LUTs or you can use this adder structure. And now we'll basically share the same routing ports. So that would actually be better than what we did here. So we'd have like a mixed block that could be either a logic block or an adder. And we don't have to add any more routing ports. We'll just reuse them. Okay, it kind of has like 2 modes of operations. But we can do even better. Okay, so that would be a better solution than what we had right now. But there's one that's even better that I'll draw. Which is essentially like, let's just build the hardened structure. But instead of saying you use the adder, okay, so let me just show what we're talking about here. Okay, so we're kind of talking about you could have LUT, 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 and you could have this big adder. And we could say, okay, we got some routing ports. They can go to the LUT, and they could also go to the adder, right? And the outputs, we could go here and have a mux, where we say you do one or the other. Okay, so that's what I mean by reusing the routing ports. You build all the LUTs, you build the adder, this 16-bit adder, and you hook it up. The inputs go to 2 spots, and the outputs are muxed. And this will now not add that much area to the logic block, and I'll have one everywhere I have a logic block, so my placement engine will be happy. But I can do a bit better than this. Instead of saying use the LUTs or use the adder, you can say, well, why don't I cascade them? Why don't I just say that I will always go through the LUTs to get to the adder? Because often I have logic in front of my addition. So I can make use of the LUTs and the adder at the same time, as long as you wanted to do something before the adder. If you didn't want to do anything before the adder, well, then you could just program the LUT to just be a pass-through. So that's fine too. Like, you don't lose any functionality, but a lot of the time you're now going to be able to, when you use the adder, you'll be able to do some LUT logic in front of it. I don't have to build more inputs. I don't have to build more outputs because I'm going to force them to be cascaded. That's effectively what hardened carry chains are doing. There's like a bunch of different variations on it, but that's basically the idea. Okay, so even better, I'll show you what most Altera chips do, and many other chips do, but there are a lot of variations on this theme. But they're all reasonably similar. Okay, so what I want to do is I want to hook up to, I'm going to call them half LUT outputs. Okay, so this half LUT output, what do I mean by that? Essentially, it's actually what Adam suggested earlier. Like, what if we decompose more? We take our LUTs and we kind of treat them as like 2 smaller LUTs. We're going to use that trick again. And we're going to use it to get little bits of logic in front of this adder. Okay, so I'm just going to do this for a 4 LUT. So remember that a 4 LUT looks like this. I've got a 3 LUT, I got another 3 LUT. There are 3 inputs that go to both those, so A, B, and C. And then their output of those 2 go to another mux with the last input D, and you get your out. Okay, so that's my 4 LUT. So okay, so here's my logic block. I take a 4 LUT up here. I'm going to treat it as being 2. I've decomposed it into 2 3 LUTs. Okay, so I take A of 0 and send it in. Should have drawn it over to the other one. Okay, let's do this. A of 0 goes there, B of 0 goes there. Okay. So this was my 4 LUT, but basically I'm treating it as 2 3 LUTs that have these 2 outputs. And I take those 2 outputs and I put them into a full adder and produce a sub output. And then I also take the carry out of that and I send it to the next adder, and I'll have LUTs in front of it and B of 1 and A of 1 and so on. And this goes down to the next adder and so on, right? So this whole thing is my new logic block with a carry chain inside of it. And I would also have a mux here, right? So maybe I'll draw that. There would be a mux that takes this signal or basically takes the final LUT output, right? These 2 things would go to a mux that's controlled by the last input and that. Okay, so I can still do a regular LUT function. I just basically bypass the adder. Or I can do an addition using hardened logic for the adds and for the carry chain. And I can still do some LUT logic before I get into the adders. Okay, and what I added is pretty minimal, right? I basically added this output mux, I added this adder, I added this piece of wire, after every LUT. That's pretty small, right? If I turn these into gates, they're pretty small compared to the LUT that I just put in, and they're quite small compared to the routing ports. And I didn't actually add any routing ports except a couple, a C in and a C out. So it didn't add much to the routing interfaces. Yeah, see how this works. Let's say I want to do A plus B, right? That was the first thing I did. So what do I put in these LUTs to do A plus B? This is like an easy question. Yeah, so you put the top function, so the top LUT function is A. So it's got three inputs. It ignores two of them, right? And just as a function of A. And it just is a pass through for A. The bottom LUT is B. Okay, so it worked, right, for a basic adder. I mean, the LUT didn't add much value there, but it didn't get in the way. Let's say I want to do a subtractor. Say I want to do A minus B. Okay, so we do that as A plus B bar plus 1 in 2's complement. How do I make this work in this structure? So what do I put in? See, I'm doing A minus B. What's the top function? So top LUT is, let's see, well, I'm doing A minus B, so top LUT is A, right? I think. Let me think about that. I guess it doesn't really matter. I guess I'm being vague. You can tell me whichever one you want, right? So, okay, so which one do you want? You want the top LUT to be, which one? Okay, so top LUT is A, let's say that. Then what do you want the bottom LUT to be? Okay, and the bottom LUT then is B bar. Okay, so that'll do a subtractor. And we also have to set our C into 1, but we can do that too. But I can do more. Okay, so clearly maybe there was like some logic in front of this. I can capture that in these small LUTs. So maybe get some more benefit out of them. But I can even see that already they've given me the ability to do subtraction. Okay, so how fast is this? This is all hardened logic. So a few gates, no programmability, right? Just wired together. So it's pretty fast. So the speed of this depends on the chip and the process, but it's typically about 10 to 50 picoseconds per bit. So it basically easily makes more than 500 megahertz for a 32-bit add. So it's no longer on a critical path. And the area of this was pretty small, and I still get to use the LUTs, so it's an area win too. Okay, so let's see. We'll see if I can finish the last thing in 5 minutes or not. Okay, let's see if I can get through this last item really quickly. Okay, so that's the basic idea of all of this carry logic. Let's look at Stratix, Intel's arithmetic in particular. So in Intel's architectures, they already have 2 registers in ALM. They can capture the 5 LUT and the 6 LUT output, or both 5 LUT outputs. because they only have 2 registers and they have these big 6 LUTs, 2 bits of arithmetic per ALM makes sense. So they don't build 1 full adder for a fractional 6 LUT, they build 2 of them. And they fracture down to 2 5 LUTs, and then they fracture each 5 LUT down to 2 4 LUTs. And then each of those 4 LUTs provides one of the inputs to one of the adders. Let's see. And then they don't add any extra routing ports, okay? So still 8 inputs coming in. They feed into these 4 LUTs that were already there, and then those feed into the adder chain. If you're interested, this paper goes through a bunch of options for how you do arithmetic, and it shows that for fractional LUTs, 2 bits of arithmetic for fractional LUTs is particularly nice. And this is a difference. Xilinx does 1 bit of arithmetic per fractional LUT. Altera does 2. This paper argues that it's better to do 2, although it's careful not to draw any negative aspersions towards Xilinx. Okay, so let's say I wanted to do this function. Okay, I wanted to do A0 plus B0, and the next bit would be A1 plus B1. Okay, so I just want to add 2 numbers. So we already just did that on the whiteboard. Okay, so we program the top, this LUT to pass through A0, this to pass through B0, this to pass through A1, B1. So it's easy, right? These are 1 input functions. So we can program them in. And we only have 4 total inputs. The ALM can handle 8, right? So it's fine, okay? So clearly we can do addition. An adder subtractor. Okay, so this is now not just a subtractor. It's a subtractor that can be an adder or a subtraction dynamically. So that function is take A plus an optional complement of B, right? So n adder sub means set the signal to 0 if you want to do an add, set it to 1 if you want it to be a subtraction, take the exclusive OR with it to B, so that basically is programmable complementation. Do that on every bit, right? Next bit is A of 1 plus n adder sub B1. Can I fit this in this structure? So what do you think? So I see Alex says yes. Okay, so let's check. So basically in the LUT functions, yeah, I can do all of this basically. I have the lower LUTs here are just doing copying through A. The upper LUTs are a function of a bit of B and this n adder sub. So that's only a 2 input function. That's fine. I got 4 LUTs. And if I count all my inputs up, I've got 1, 2, 3, 4, 5. 5 is less than 8. So it all works. Okay, so that looks good. So I'm getting some good use out of these LUTs. What about if I said A0, I'm going to add A and either B or C. Okay, so I want to mux between 2 different things, B or C, and then add it to A. Is that going to work or not? So you have to first think, like, will it fit in the LUTs? Okay, so A will fit. Can I fit the mux of B and C in a LUT, in a 4 LUT? I see some people nodding. Yeah, what do you think?
It's like if it's a fractional 6 LUT, like the 2 extra.
Yeah, so this one is fun. Okay, so the way you look at it is, okay, so again, I basically take, what have I done here? A or B. I need to fix this figure. Okay, so what I actually did is A or B muxed plus C. Okay, so I just flipped the variables, but you get the idea. I'll fix it afterwards. I'll eat a chocolate bar for finding my own mistake. So yeah, I've got a mux function, which a 2-to-1 mux just needs 3 inputs, right? So here it should have been B and C, but it's A and B, and I've got a select signal. Same thing up here, and then the other input just passes through. So I don't exceed any LUTs, and if I add up my signal counts, it's 1, 2, 3, 4, 5, 6, 7. So 7 is fine. So I basically captured some logic in front of my adder. I'm starting to capture a reasonable amount. What about this? Could I take select from 2 signals and then add them to the selection of another 2 signals? Would that work or not? Yeah, so my LUTs are fine, but I got a problem with my inputs. Okay, so if I add up all the inputs here, I've got 1, 2, 3, 4, and there's a select signal, actually 2 select signals. Well, I guess if it was a shared select signal, then I have 1. But I have at least 9 signals here. This won't work. So But basically, you can get a reasonable amount of logic getting pulled into these LUTs. So it's a good low-cost way to reuse them. One thing that you also have to do is check that you don't run out of inputs in your logic block. Okay, so this is the most complicated one that I've done so far. Add A plus choose B or C. And they're all 32 bits. So if we take Stratix 4, it's got 52 inputs, and it's got 10 fracturable LUTs. So that means I can do 20 bits of arithmetic in every logic block. So if I add up how many inputs I need 20 bits of A, 20 bits of B, 20 bits of C, and a select bit. Okay, that's 61 signals. Okay, so 61 signals is too many, right? I only built 52 signals. I don't want to build a whole bunch more routing ports just to make this work. It would be too expensive. So it's fine. I can just tell the CAD tool, don't do this, right? When you see this, these have to go in LUTs in a different logic block, and that's perfectly fine. But Altera came up with a clever solution to allow this to work, just for more efficiency. So what they, yeah. They're 32 bits, but I can only do 20 bits per logic block. So I could have made them 20 bits. I guess I did, right? But in the end, I'm only going to check this 20 logic block by logic block. Yeah, so I'm counting the inputs per logic block. And for this Altera logic blocks where they have 10 fractional LUTs, which means 20 bits of arithmetic, I'm only going to get the first 20 bits of each of these things in the logic block. And then we'd have to go to another logic block. So Altera has a clever technique of how they do this. They basically built a little bit of extra muxing, but it's very little. So basically, you can either use the whole carry chain, which is what you usually do. So you go through 20 bits of arithmetic, and then you leave the logic block, you go to the next one. This is all dedicated interconnect, so it's very fast, including this interconnect. So it's all not programmable. There's a tiny bit of programmability of you can actually choose to leave the logic block after 10 carries instead of 20 and go to the next logic block. So just one SRAM cell, one 2-to-1 mux to make that choice. So they call that the early exit carry chain. What it means is if I actually had the opportunity to pack a really complicated carry chain in here, I could do it, and I won't run out of inputs as long as I only pack 10 bits at a time. And I can pack 10 bits at a time because I have this option to leave early. Now, these other ones, I'm just going to use their LUTs. Okay, so I can't use them as part of this carry chain, but I can use them for other things. And I did use up a bunch of my inputs. In this case, I would have used up 31 of my inputs, but that still leaves me with 21 more inputs. I can probably find some low complexity logic or tightly grouped logic to go in here. Okay, and that's the last trick. So that's the end of the lecture. Thanks, everybody. Grab more Halloween candy if you want on the way out. So.